Do, do. Okay. Um. Okay. So this is going to be another revision session. This is going to be the final one I'm going to do, sadly, for paper 3. Um. But I think the revision session I'm doing now and the other two, the stats and mechanics I did previously, which should also be on my channel as well. I think that'd be good preparation. Now, with that in mind, I picked. We're going to go through another stats and mechanics paper. Now, the stats is from 2023. I picked that because I think it has some more interesting questions that are slightly different to the 2022. But all in all, if you practice a few stats papers, they're most of the same. Same with the mechanics. I picked mechanics as well, which was from um, November 2021. There we are. Um, but yeah, but the other two papers I did for 2022. So yeah, this time I'm going to try this one. We're going to go over it. Cool. So question 1. So we're given a Venn diagram. Pretty typical question about Venn diagrams. We're given some probabilities about 3 events A, B, and C. Um, Hang on, let me try and move back a little bit. Try and make sure my fan, because it's absolutely boiling. Try and make sure I'm away from the fan a little bit so it's not as noisy. Okay, so we've got these probabilities, and the first one is simply to find P of A. Now, the probability of A is simply all the numbers in the circle of A. So it's simply going to be 0.13 add 0.25, and that'll be 0.38. There we go, nice and simple. Then we're given the event P and C are independent. We need to find some values. Now, independence then, I'm going to do part B down here. Actually, I did A over A. P of A was 0.38. Part B, so events B and C independent, what that means is that P of B times P of C, so their two probabilities times together, gives their intersection, so the probability of B and C, which is denoted by this. So now we can kind of work expressions for all the 3 of these parts, right? So first of all, probability of B, all the numbers in the circle B, which is these 3. So we can add them all together. So it's going to be 0.05 add 0.25 add add 0.3. And then we're going to times by the probability of C. Now that's all the numbers in the circle C. Right, so this and this. So it's 0.3 add P. Okay. And that's going to equal the numbers that are in B and C. So the overlap between B and C is simply just 0.3. And so we can solve this equation. It is a linear equation for P. So let's just simplify this bit. So 0.05 add 0.25 add 0.3 would be 0.6 times 0.3 add P is 0.3. So let's expand the bracket. So 0.6 times 0.3 would be 0.18 times 0.6p gets us 0.3. Therefore, 0.6p is 0.12. 0.3 minus 0.18. Well, then simply p is going to be 0.12 over 0.6, and that will give us 0.2. Cool. Then we need to find Q. It's around the Q is the number outside the box. Circle, sorry, it's inside the box. Now, every number in the box, all the probabilities have to add up to 1. We have to include everything, right? So that means all these numbers in total, right, all of them have to add up to 1. That means that 0.13, and this could be quite long, 0.13 add 0.25. Well, actually, first we can kind of make it a bit easier for ourselves because we know that these three numbers add up to 0.6. We've worked it out already. So 0.05 and 0.25 and 0.3. That's these numbers in B, they add up to 0.6. So 0.6, then the other numbers are 0.13, P and Q. So 0.13 add P and Q. Now P is 0.2 add Q, that's add up to 1. But therefore Q is simply 1 take away the others. 1 take away 0.6, take away 0.13, take away 0.2, and you get 0.07. Cool. Then it says for part C, from the probability of A given not, I'll do that here. Probability of A given not B. That's what that line means, given. So the total, we're considering that B dash. Now B dash here means not in B. So all this circle B here, we want all the numbers outside of it. Okay, so that's going to be this number P, this number Q, and the number 0.13. So given B dash, so that's these numbers are circled, so that's our total. So out of those numbers, so 0.13, well, I know these numbers add up to 0.6. So it's just going to be 1 take away 0.6 and 0.4, okay? Which is these three numbers added together, 0.13, P and Q. So from these numbers, we also want a number that's in A. Well, in A, it's 0.13. So that's our probability. So 0.13 divided by 0.4 gets us 13 over 40, and that's our probability for part C. So I'd say that's P, A given, not B. Again, that's what that symbol means as well. B dash or anything dash means not B. Okay. Cool. Question 2. A machine fills packets with sweets and a seventh of the packets also contain a prize. The packets of sweets are placed in boxes for being delivered. There are 40 packets of sweets in each box. The random variable TF is the number of packets of sweets that contain a prize in each box. Okay. State and condition needed for T to be modelled by the binomial distribution of 40 and a 7th. Let's have a look. Okay, so if we are modelling binomially, in general, you need a fixed number of trials. You need a probability of success. But you also need the events to be mutually exclusive, not mutually, sorry, independent, which means the probability of picking a given suite which has a prize, or the suite like they don't affect each other. So like if you pick, how do I explain this? So independent meaning all the suites essentially have the same sort of. They're all random, right? That's the assumption. It's random, so they're independent. Like all the suites that you pick up, uh, the probability any of these suites has a prize, it's always the same, right? So the what picking some sweet packets don't affect the probability of another sweet packet and a prize. You know what I mean? So they're independent. So the assumption is the packets of sweets and with a prize have to be independent, but also it's random the probability. So random, it's random that we're picking a packet of sweets that has a prize. You know, we're not being biased essentially, and that's essentially what we could say. Uh, so, uh, so this 40 here, the N that we're picking, the number of trials, those are the packets of sweets in a box. So we're going to say the probability of picking sweets. How do I want to phrase this? So the probability of picking sweets with a prize is independent. No, the events are independent. It's always a seventh because it's random. Okay. But that comes as well from so the event of picking a sweet with a prize, and obviously the other event of picking a sweet without a prize, with a prize and no prize, is independent. Okay. Okay, so that's the assumption. There's a fixed number of trials. Probability of success is fixed, I guess. But that also becomes from the fact that the probability is random. Yeah, the probability is the same if for any number of trial. The probability of picking a sweet with a packet will always be seventh because it's random. I'm not being biased with sweets and packets I'm picking as a prize, and it's truly random. And also, it's independent and as well in the sense that the event of picking a sweet with a packet and a sweet with a prize and the sweet without a prize, they're independent. They don't affect each other in some way. So the probabilities don't affect each other. They're not dependent. There's no conditionality or something like that. Anyway, a box is selected at random using that binomial distribution. So I said part A up there, so I'm going to do part B. So we have T, which is binomially distributed, 40 at the seventh. On the probability that the box has exactly 6 packets containing the prize. So the box has 40 packets, so the probability of 6 packets having a prize is going to be T equals 6. Okay. And that is going to be on your calculator. So now we can start using the calculator. Let's go to menu 7. And you got it on the binomial PD because that will give you the exact the number, the probability of just a fixed number. So T equals 6. So you have a probability of binomial being equal to something, not less than or equal or greater than. You want PD. So our number is going to be 6. N number of tries is 40, and the probability is 1/7. And so then the probability we get is 0.1727, blah blah blah. Okay. And then that's part I, part II. What the probability that a box has fewer than 3 packets containing a prize. So we want the probability of less than 3, right? Because it has to be fewer than 3. But our calculator only works with probabilities when it's less than or equal to. We need it to be less than or equal to. Well, because it's binomial, it works in integers only. So 1, 2, 3, actually starts from 0, 1, 2, 3, blah, blah, blah. So if it's less than 3, then the next number down will be less than or equal to 2. And that's what we're going to put in the calculator. So then, because it's cumulative, because we want to add up the first few numbers, we're going to go back to our table. Now we're going to scroll down to binomial CD, which is cumulative distribution variable, and then X is going to be 2 now, and then that's all the same. So then that'll be 0.061 587 blah blah blah, and there we are. Okay, cool. Camille's Sweet Shops buy 5 boxes of these sweets. So what's happening is we only worked with 1 box originally, but the box had 40 sweets. So we worked with how many sweet packets there were in 1 box. Now what's happening is we have multiple boxes. So then the probability of 2 of these 5 boxes and fewer than 3 packets. Well, we want the probability of a given a given box having fewer than 3 packets. So that's part II. So then if we have a new binomial distribution, say y or x, whatever, binomial NP, so n is now the number of boxes 5, and the probability of a box then that we choose having less than 3 packets of prize is this part III. Part II, so it's going to be this number here, 0.06. I'm going to say 16. I'm going to leave it there to round it. Okay. And then we want the probability of that being, what does it say? Exactly 2. So again, that's going to equal 2. So again, we're going to go back to our calculator. I'll tell you what I'm going to do. I can get the exact answer, the probability we just worked out by storing it as this number A here. Then if we go to 7, again, we want binomial PD now because we're equaling a number. So x is going to be 2. N is going to be 5 now. And P is going to be our answer A, which if we then click alpha into make it the red mode, because A here is a red letter, so that we need it to go to red. There we are. That's our probability exactly. So then P is going to be 0.031 34 blah blah blah. Cool. And there we are. Part D. What's it saying now? Camille claims that the proportion of packets containing a prize, so now we're going back to the packets again, is less than a seventh. A random sample, 110 packets taken, and 9 packets contain a prize. So it's going to be a binomial hypothesis testing, right? So again, we're going to need a null hypothesis. So that what we're testing is probability, aren't we? Because we're saying the proportion or the probability of the packet for the prize is less than the seventh. So the null hypothesis H0 is going to be nothing's changed. So the probability will still be a seventh. And then H1, well, we're specifically saying the alternative is that there is a difference, but specifically the probability is less than the seventh. So P, the probability is less than the seventh. And that's what we're testing. Okay, so how are we going to work that out? But I think the way I like to do it is just do a critical region. Because some questions might ask you to do a critical region. So if you do it like just computing probabilities, that might be okay, sure. But critical regions is a more flexible method for the questions I might ask. But anyway, so how are we going to find this critical region? Well, what's going to happen is, again, there's almost like a normal distribution, right? We want essentially our critical region. We want the value of x, right? The number of sweets, such that any sweets before it, the probability is going to be the significance level, which is 5%. So that's going to be 0.05. Now, because it's only a one-tailed test, we're only working on one side. We don't halve it, okay? That's simply 5%. And what that's saying is then, if we find this x, which has got the critical value, anything less than that, but give us a weirdly small amount of sweets with the prize, so there's something gone wrong there. So the way to work that out then is say, well, we know the probability of x being this number, I'm going to call it A, x being less than or equal to A, that probability has to be less than 0.05, okay? But then what we're going to do is use, obviously, the calculator to binomial CD, and then we're going to start just testing some values of A, or X, sorry, or A, or whatever. I'm going to start with 1. That's a small number. Start small. N was. I need to state my binomial, don't I? X is binomial. N was 110, wasn't it? Yes, 110, and obviously the probability is still a 7. So then we're going to use that parameter. So 110 and 1 divided by 7. Okay, that's 10 to the minus 7. That's going to be far too low. So let's consider 4. That's still far too low. What about 7? That'll be 0.007. So that's close though. So I'm gonna say probability x less than or equal to 7 is equal to 0.07. No, 0.07. Sorry. Because that's in standard form, right? Depends how you calculate does it, but this one clearly gives it standard form. I can't convert it as an actual decimal number, I don't think, but I just need to have to read the standard form. So actually, that is above 0. No, it isn't. Sorry, that's still quite low actually. Okay, I'll leave that there. I'm not going to rub that out. And let's test some. Okay, I need to go a lot bigger then, don't I? Let's try 12. Ah, there we go. So we have 0.19. That's far above 0.05. Let's try 10. 0.07. Let's try 9. 0.03. Ah, there we go. So I'm going to note that probability x less than or equal to 9 is equal to 0.03. 8. Okay, I don't really care about the others. And then when it was 10, that's going to be. Oh, that's going to be 0.0718. So clearly, between 9 and 10, we've exceeded the significance level. So we've gone above 0.05. So the last value that here, which is the last value to give the area or the probability of 0.05 or below, clearly A is going to be 9. So critical region is x less than or equal to 9. And what that's saying is then if there are 9 or fewer packet of sweets with in the sample 110 that have a prize, then there's something gone wrong there. So actually, there's evidence to say because it's quite small, really, with that probability anyway. So it's saying, oh, actually, there is enough evidence that actually the probability is less than. Let's have a look. So we have 9 packets. Well, that's bang on the critical region. So 9 equals 9 lies in the critical region. Lies on the boundary, actually. So 9 lies in critical region. Therefore, there is enough evidence, so significant enough, to reject H0 and therefore accept H1, which means there is enough evidence to suggest the probability is less than a seventh. There we go. There we go. Cool. There we are. Was that the whole question then? It was cool. So that's just a standard hypothesis test. But I do like critical region. I think it makes more sense to me as well. I don't know. I don't know. And this sort of thing works with all hypothesis tests, at least for the A level, the normal A level. The idea that you form a critical region with a certain probability or whatever, and then you can use it to find the region. Anyway, we'll be seeing another one in a minute as well. Question 3. Ben is studying the daily total rainfall in Leeming, and we're given some data. Explain how the data need to be clean before Ben can start to calculate statistics, which is the mean and standard deviation. So cleaning essentially means the data has to be usable, I guess. But the thing here, all these are fine, That's fine, it's grouped. But this is a bit weird, this trace. That's not a number we can work with, so we need to clean it, so-called, um, to make sure we can actually use it, right? So that's cleaning. But trace is actually a number between 0 and 0.05, so it's a very, very small number, but it's still non-zero. So we have, so yeah, so essentially we need to convert trace to t. So that's how we would clean. So I guess we would say we need to we not convert. We need to I guess convert x equals trace to x to 0 less than x less than equal to 0.05. To be able to use the data, as trace is a very small non-zero number, right? Now you don't actually have to remember the actual range, I don't think. I haven't checked the mark scheme. It's a very small non-zero number. Uh, but you need to but you do need to be aware that trace is a very small number though. Then that's from the large data set. When I did the 2022 paper, there was a question about this as well. So that's how I remember it. But let me have a look at the mark scheme for that then. I think that's I don't know. What exactly are they looking for, I wonder? Question 3. Need to replace trace with a numerical value. Yeah, so it's the whole idea of making the data usable to calculate. So you need a number. And then it says you give a value to suggest for trace, which is between 0 and 0.05. Okay, so you do need to give a number then. Okay, but really you could say, if it's a very small non-zero, you could say something like 0.0001, something like that. That would be fine. But you do need to be aware of that, but there we are. Cool. Okay, then it says using all 184 of these values, Ben estimates sum of x squared. And we've got those values. Then we need to work out the mean and the standard deviation. Again, very typical question. So the mean, first of all, you need to realize the mean, which is x bar, that's going to be the sum of the values x over how many there are. That's kind of like G's and C, right? You somehow got the frequency times get the sum of the frequencies divided by how many you have to end the size of the sample. So the sum of x then is going to be 390, and the n was given to be 184. So then that would go to 195 over 92, and that I guess would be 2.122 dp, and that'd be what, in millimeters, because it's rainfall, isn't it? Yeah, x millimeters. Okay. Okay, cool. And then the standard deviation. Now this one you don't actually really have to learn. Hopefully you used it and you've worked with it enough already, so you have an idea. But it's in the formula book. But you do need to know how to realize what it's saying, because because it's given like this here. So the standard deviation, and you're going to want to work with this because it says the mean of x squared here. So it doesn't give it in terms of sum of x over n. It says it's the mean. But anyway, so that means the standard deviation, sigma, is going to be the root of sum of the values all squared over n minus the mean squared, right? So that's going to be, what's sum of x squared? That's going to be 4336. So the root of 4336 over 184 minus the mean. Now the exact mean value was 195 over 92 all squared. Remember that's sum of x over n. And so we put that in the calculator. You get and we get this number here, 4.367 millimeters to 3 dp, I'm going to say. Cool. I probably should have made it consistent because I rounded this to 2, but I don't think they're that bothered. I'm pretty sure that that'll be fine. Longer than at least, I don't know. Anyway, that's it. Ben suggests using the statistic calculated in Part BI to estimate the annual mean daily the annual, and that's going to be key annual for Lehman. Now, so this was also for Lehman in the same year, but we only picked 184 days. Now, which days did they pick for this? Well, actually, you should remember it's between May and October. And that's something you need to learn. That's part of the data set knowledge. Well, that's the summer months, isn't it? So, first of all, it's not suitable because to calculate if you want to use it to calculate the annual, um, it's not suitable as you kind of like extrapolating the data because you're using it to assume other values that are outside the data set, so outside the months you studied. So it's not suitable as the data study or the data is only between May and October, and that's just something you need to learn. But if you remember the months, that sort of range of months, it's usually May and up to October anyway. For the UK stuff anyway, between May and October. So not reliable for other months of the year, right? And then the second part's asking why is it not reliable for the rest of the year, basically. How would you expect it to differ, essentially? So why would there be a change from the actual mean? From the actual, so the actual annual, what would that compare with the mean of these 100 and what was it, 84 days? Well, like I said, if you're considering every single month, we're only working between May and October. Those are like the summery months, the warmer months. Well, if we include in the other months, like November to like April, those are sort of like the wintry, colder months. So the annual rainfall is going to be more. So what I'm going to say is the annual rainfall mean, so the mean amount of rainfall in the year would would be higher than the mean we calculated, as it would include the winter months or slash the colder months, which has more rain. Okay, and there we are. Cool. Um, okay, question 4. Um, A study was made of adult men from region A in a country. It was found that the heights were normally distributed with a mean of that and a standard deviation of 0.8. Okay, so it's just a simple probability. So a proportion of men that's all 180. So let's say we have a normal distribution x, which mean of 175.4, and a standard deviation of 6.8, but we're going to want that squared, all right? That's how normal distribution works. So then we want to use that well to find the probability that the height, the x, is going to be taller than 180. So then we go back to the calculator. Oh, Go to menu, go to 7. Then we want the normal CD because it's a cumulative. You wouldn't want the PD one. And so then it says lower and upper. So the lower limit is 180, right? So we're going from 180, but there's no upper. We want every value above it. Doesn't matter where it stops. So the upper, you just call it a big number, say 10 to the 50. Okay, that's a very, very large number. It's basically infinity. All right. If you have no lower limit, it would basically be negative infinity. So it's about negative 10 to the 50. But then as standard deviation was 6.8, not 6.8 squared, because it's just asking for sigma, not sigma squared, remember that. And mean is 175.4. And so our probability would be 0.24937, blah, blah, blah. Cool. Then it says a student claimed that the mean height from a different region is different to the region A. The random sample 52, I'm going to highlight the numbers. The mean height of 177.2. The students in the standard deviation was the same on both. We want the hypothesis test on this. So, hypothesis testing on the mean, again, a pretty typical thing. And again, there's two ways of doing it. I'm going to try and do the critical region way. So again, we need to write our hypothesis. So I was saying that there's no difference in the mean originally. So the mean will still be 177.2. No, sorry, that's the sample mean. No, sorry. If it's the mean of A was 175.4. Sorry, my apologies. Because that's this sample from B, but we want to say that the mean from A is not different in B. So originally the mean was the same. And then H1, that the mean, okay, is it going to be less than or greater than or neither? Let's have a look. What did it say? That the mean height of in the region B was different. So it doesn't say less than or greater than the height, it's just different. So it's simultaneous, so it's just not equal to. Okay. So the mean simply has to not be equal to 175.4. So that opens up to a two-tailed test. Okay. So what am I going to say? Well, again, I'm going to formulate my normal distribution. So I'm going to say, and in particular, we're looking for the means, right? So what we're going to do with this sort of distribution is look at how the means are distributed. So the probability like same sort of thing, but this time we're going to be doing like the means x bar, okay, and how the mean will change. Okay. So what we're going to do then is we're going to say x bar now. So the mean distribution is going to be normal, and we want the sample size mu. No, we don't. Sorry, no, sorry. We're assuming the mean will be the same. It's like the binomial. 175.4, and then the standard deviation will not necessarily now be what was it, 6.8. We want the standard deviation adjusted for the sample. So that's going to be the original standard deviation over n. Okay, so now we're kind of shifting the standard deviation to 200 to 52 people. So that's n. So it's going to be 6.8 over 52. And 6.8 squared over 52, I should say. Um, okay, and that would be your mean and variance for the mean distribution of x. So the mean distribution again is just saying how the means are distributed. And so what we can say with this mean distribution is what is the probability of of a mean being not what we're going to say is actually again have a horrible curve. Something like that. Say if you have a mean here and we want it on either side, because it's two-tailed, either side is going to be 0.25. So that's going to be 0.025 that side, 0.025 that side. And what we're saying is, with this mean, I'm going to call it A bar and B bar. I want to say about how these mean of X bars distributed, the means are distributed, right, in the sample. What is the probability of the mean in the sample being less small here, A, small enough such that the probability before it is 0.025 or lower? In the same way, a probability that's so high on the other tail, this mean B, what's the probability that the mean in the sample is now going to be greater than less than 0.025 on the other end? And those bounds, those critical regions, are the critical values A and B, and that's what we want to find here. Okay, so how are we going to do that? Well, we're going to want to say, first of all, probability that, again, X bar is going to be less than or equal to A bar, or just A, it doesn't really matter. And that's going to be a probability that is less than, well, it's going to be equal to 0.025, isn't it? Because that's like a cumulative, right? And we want the area under the below it, before it, to be 0.025. Because remember, it's a 5% significance level, but we're splitting up into two. Anyway, so how are we going to find A? Well, if we know the area between that point, and we know the mean and the variance, the standard, well, yeah, with the variance, well, we can just use the inverse normal because in the function in the calculator. If we go back to 7, because the inverse normal says, well, if we know the area and probability, we work backwards to find the value that gives that probability, which is A. Anyway, let's go back to menu 7. Menu 7. And then what the inverse normal. So we know the area is again 0.025. Sigma is going to be 6.8 squared. How am I going to say this? 6.8 squared divided by 52. That's the variance. And the mean is again 175.4. So our x inverse is therefore using inverse normal. A is going to be 173.66, right, to 2 dp, and that is your critical region at this tail, at the lower tail. Now we're going to say the same thing here. We also want to find the number probability. Let's do it down here. We also want the probability of another number, the mean, again, the mean distribution, the mean in the sample to be greater than or equal to another, some sort of other value B. We also want that to be 0.025. So anything higher than the mean B will again be 0.025. So this here. And again, we can use inverse normal. But this time, the inverse normal only works again for less than or equal to, particularly. So what we're going to say, well, if this area is 0.025 on the right here, then anything before it's going to be 1 minus 0.025. Okay, so that's the same as saying probability that x bar is less than or equal to b is going to be equal to 1 minus 0.025, and that's going to be 0.975, right? And that's what you're going to want to say here. So then if you use the inverse normal, so the area, well, the mean and variance are the same, so it's going to be 0.975. And so then we get the B value of 177.14. 4, I'm going to say, against 2dp. And I'm going to say by inverse normal, again, to show how I did it. And so those are our critical values then, critical values. So the critical region is, again, the mean is either x bar less than or equal to, what was it, 173.66, or x bar is greater than or equal to 177.14. Okay, now we can compare that to the mean they've given. Now the mean they've given was 177.2. So 177.2 lies in the critical region. So 177.2 is greater than 177.14. So lies in the critical region. Now, hang on a second. Oh, hang on a second. I've got my numbers wrong. Hang on a second. Wait, is my sample right? 52. Let me go back. Let me 6.889. Okay. 175.4. That was the mean, right? Let me check my numbers. No, it should be fine. Hang on, what have I done here? That's interesting. Apparently, okay, apparently you can't accept it, so it shouldn't lie in the critical region then, apparently. Why is that? One seven seven point two. But 177.2 is greater than. It's interesting, that is. Uh, hmm. I feel like I put something in wrong then. I don't know. I'm pretty sure it's the right. That's the right approach. The method for it. Alternatively, what you could say is, okay, let's do it the other way. I'm going to say or simply the probability of x bar being 177.2. So 177.2. Okay, alternatively, so then if you compute that probability, let's go back to menu 7. It the normal CD, so then the lower limit 177.2. The upper again, the mean and the mu will be the same. You get 0.0, yeah, 0.021. So that'd be less than 0.025. So that should also be in the critical region. So what's going on here? But they get 0.028. So what have we done here? I've definitely copied something down wrong, for sure. Let me have a look. So that's the distribution you work 175.4, 68 squared over 52. And then you want the probability of S bar being greater than 177.2. They get 0.028. What am I putting in wrong? Let me compute this again. So the sig. Oh, that's why. Oh, I'm such an idiot. I forgot to square root it. I forgot to square root the bloody sigma. There you go. Lesson learned. There we go. Okay. So that will affect our critical region. Okay. Okay, so yeah, the calculator, I did that as sigma, but the calculator, yeah, obviously you have to square root it. Oh man. Okay, there we go, that explains it. So the method is right, you just need to square root it. So the root. So if we do root of, first of all, 6.8 all squared divided by 52. Oh, I'm probably get a syntax error. What have I done now? 6.8 squared. Oh, single bracket. There we are. Okay, so now, okay, that's the normal. I don't want the normal. I'm going to go back to a critical region. So we want to inverse it, given the area. We want that's our sigma now. So the lower tail. So that'd be B, wouldn't it? So B with a probability of 0.975. B would be not 177.14, but 177.25. Okay, so 2 decimal places, and then I'm going to do A again. So now instead of the area of 0.975, it's going to be 0.025. So that's going to be 173.55. Okay, there we go. So now our new critical value, there we go, is 173.55 to 177.25, and the mean 172, was it point? What was it? 177.2 is now less than 177.25, so it does not lie in the critical region. Okay, hopefully you can see that. So it's not less than 173, but also not greater than 177.25. It's 20. Therefore, there we go. There is not enough evidence to reject H0. So insufficient evidence to suggest mean of heights in area B, was it? I don't know what it was. Area B is different than area A. Okay. Ah, there we go. What silly error, man. Silly. But that is a good learning curve. Make sure, because that probably is a common mistake, make sure you square root, when you put it in the calculator, you square root your variance. So your standard deviation is what the calculator is asking for. The standard deviation is the square root of the variance, which is this number here. Okay. Okay, got there in the end. Okay, cool. Then it says for part C, find the p-value of your test in part B. So the p-value is essentially the probability of of the height being 172.2 essentially. So the P is the probability of, well, X bar being 172.2. And that's going to be, if I, no, sorry, greater than or equal to, not equal to. And that's going to be, then I'm going to have to do the normal cumulative function. So then that's going to be the lower of 172.2, the upper of that, so that would give us, no, but we have to do one minus, no, that should be fine. Why is it going to be such a large, that shouldn't be the, oh my god, the upper limit. Why is it giving me such a large number? That doesn't make any sense. If it's greater than, it's basically by the critical region, isn't it? So it should be like 0.28 or 0.25 or 0.26 and something. They've got 2.8. So why have they got 0.99? What's going on here? What have I inputted wrong now? So the lower limit would be 172.2. The upper limit would obviously go to infinity. The sigma value was 10. And I made sure to square root it this time. The mean is still 175.4. Obviously, you might think, well, why didn't I adjust for, you know what I mean, like I did in part B, where I adjusted for the fact that it's greater than, so I made it one less than. But that shouldn't need it because we've already got lower and upper limit, so that shouldn't matter. 172.2. Trying to wrap my head around it. Oh, it's one. It's not 172. I've misread it. It's 1177.2. There we are. What a shambles. And that's 177.2 there. I misread it. The mean height was 177.2, not 172.2. What a mare. Okay, so the probability of 177.2 should now be a more sensible number. Okay, 177.2. There we go, 0.028. That seems fairly close to the other critical region of 0.25. 0.02 2814. Something right? Okay, I'm gonna leave that there. But that's not the p-value. Well, that's the probability of the x being that, right? Um, uh, 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 oh, that's a really wonky graph. Here, right? So obviously the critical region was up there. So the probability of x being the actual mean, 177.2, is 2.814. However, what we then need to do is adjust for the fact it's a two-tailed test. Because we're only working on one tail now, so we need to double it. So I'm going to say that's a half p. So then p is simply two lots of that. So then that's going to be, if I put that in the calculator, 0.02814 times 2 would be 0.5, 0.05628. There we go. Okay. And so what that's saying is the p-value on that particular tail. of the fact that the probability of the mean, according to what model and stuff, the probability of the mean in that sort of the mean in that particular sample, is actually going to be 177.2 or higher. So it's 5.6%, adjusting for the fact it's we're only looking at one tail, whereas this probability coming from the fact we halved it because it's a two tail. Okay, so that's the p-value. It's a really weird question that is. I don't ask it very often. That's just something you need to know. Okay. Um, but yeah. Anyway, question 5. Let's get away from that question. Oh my god. What a nightmare that was. It wasn't difficult. It's just sort of writing the wrong stuff. See, these are sort of small errors you got to look out for. Make sure you read the numbers you're writing down. Anyway. Tissam is playing a game. She uses a ball, a cup, and a spinner. The random variable x gives the number of spinner lands when it's spun. And then we give the probability distribution x. So this is fairly common as well. You need to know how to work with a probability distribution table like this. So if you have a value of x, then the associated probability of choosing the x value is this. Okay. A, B, and C are probabilities. To play the game, a spinner spun to obtain a value of x, which I guess means it's because it's random. Well, I mean, the spinner might not be random, but anyways, then it says Tissam then stands X centimeters away from the cup and tries to throw the ball in the cup. The event S represents the event that Tissam successfully throws the ball. To model the game, we are given that probability S given X is K over X, and S and X is the same value, regardless of the value of X. Using Tissam's model, show that C is 8 over 5B. So what that means is essentially to consider and work with the probabilities in the table. That's a fairly common strategy. Well, we can't. Well, the only probabilities we've got are like A, B, and C. That doesn't tell us anything, So what we're going to work with is this information as well. Now, what's funny is we are given probability of S given X, right? I'm just going to say it like this. That's funny. We're given the conditional, but we're also given the intersection. This formally should know relating the intersection of two events, S and X, and if the conditional probability is S given X. So if we are given X, then that means we already assume the probability of X to be the total. Then we need to work with the probability that X occurs and then S occurs. So it's S and X. But we're given these two already. So if we rearrange, that means probability of X is P of S given X times P S and X. Okay. And we're given information about both of these. S and X is K over X, isn't it? Which is here. And S and X is just a number, it's a constant, it's the same value. So that could be equal to K over X, and then this will be a constant, which should be the same. So that would be, let's call it, I was going to call it K, now let's call it T. So then that will be equal to K T over X. Okay, cool. Well, P of X then, that's cool, but we know what probability of X is, it's in the table. Let's work with it. In particular, we need to consider C and B. So I think then, let's work with the table. So let's consider P of B. So how are we going to get probability of B? How are we going to get B the probability? Well, we're going to choose X as 50. And then when we choose X as 80, we're going to get probability of C for P of X, okay? So that means probability of 50. Oh, so when X is 50, I'll just say, to be more clear. Well, that's going to be, using this formula here, KT over 50. However, we also know that's going to be equal to B because that is the probability of X is 50 from the table. In the same way, probability X is 80. That's going to be kt over x, which is 80, and that's equal to c. Now, actually, we've got some sort of simultaneous, so therefore we can say that we've got some sort of simultaneous equations. So what we could say then is kt over 50 equals b and kt over 80 equals c. Well, we've got kt is common in both, so kt is equal to 50b. Therefore, we can substitute it into here, into the c equation to get 50b over 80 equals c. And so that means 5 over 8b, if we cancel that down, is c. But we want c in terms of b, so we just need to divide by 5 over 8 instead. So then c is 8 over 5b. And there we go, that's our result for part A. Cool. Then we said to find the probability distribution of x. So obviously we're already given the distribution, we got all the probabilities, but it's asking to find the missing values A, B, C, and D. Now there's not much to work with, but the only other thing we can do is do the same sort of approach, right? So we considered 2 of the probabilities already. Let's consider the other 2. So x is 20. So then that's going to be equal to kt over 20, which is going to be A. And then probability x is 100, is it? The last value up here. Well, that's going to equal D, probability of D. But that's also going to be kt over 100. And that's going to equal D. Okay. Okay, so what's the strategy going to be here is, so we've got more equations. Wow, what we also know is that all of these probabilities have to add up to 1, don't they? But we also got 4 equations. So I think if we can get all these equations in terms of just B or C, then we're going to get all of these in terms of one letter C, and we can add that to 1 to solve it, I think. I think that's the strategy, but hopefully it made more sense as we go along with this. So we got in terms of KT again, in terms of A and B, D, but we know what KT is. That's 50B. So therefore we can then say that A is going to be 50B over 20. So that's going to be 5 over 2b. And likewise, D is going to be 50b over 100. So that's going to be a half b. But now I can substitute that in. So therefore, so this is B here. Then A we saw was 5 over 2b. C was 8 over 5b. We worked out before here. And then C was a half b. And now, all these are the only 4 probabilities, so they have to add up to 1 in total. Well, we can just add all of these are now in terms of b, so now we can add it all together to 1. So what we can then say is that therefore 5 over 2b add b, add 8 over 5b add a half b, was it? Equals 1. Was that the values? Let me check. 5 over 2, 8 over 5 and a half, cool. Well, that's just not simultaneous, it's a linear equation. So that would be 5 over 2, add 1, add 8 over 5, add a half. So that's going to be 28 over 5b is 1. Therefore, b is going to be 5 over 28. Okay. So what did it ask for then? Yeah, find the probability distribution. Okay. So that's 5 over 8. So let's rewrite the distribution then. So we have x and probability of big X equaling x. So we had 20, 50, 80, and 100, right? So B is 5 over 28. So then A, remember, was 5 over 2. Lots of B. So it's 5 over 2, 5 over 28. So that's going to be 25 over 56. And so C, remember, was 8 over 5b. So 8 over 5. So that's 5 over 2b. That was half b. So 8 over 5 times by 5 over 28 will get us 2/7. And then 100 would, a half of b, it's going to be half of 5 over 28. And so we get 5 over 56. Okay, and that should be the complete probability model. Hang on, what have I done? KT over 20. Hang on, so what have I done now? KT is 50b, so 50b over 100, that should be half b. I copied something down wrong again, oh my god. So 5 over 2b, add b, add 8 over 5b, add a half. Hmm. Um, uh, they got 2/5 and 2s. They took the reciprocal. Why? Man, this doesn't make sense. What have I done here? What? This doesn't make any sense. C is equal to 5 over 8b, then it says 8 over 5. Hang on. I just realised that that's a bit silly. What have I done here? God, this is shambolic, this is. I do apologise. But it's good we're going through these errors now to floor them out. So KT should be 50b, but just times by 50. That should be fine. Then KT over 80, so KT is now 50b. So KT is 50b, so then KT over 80 is also C. So 50b over 8 is C. That'll go to 5 8. So then you want 8 over 5. Okay, I think there's a little bit wrong with the T here. Have I rearranged it right? I haven't rearranged. I'm so. So I do apologize. This is wrong. I rearranged it wrong. I don't know. I don't know what's going on today. Uh, no, that is wrong. That's why. Everything that. Well, the rest of the maths is the same idea, but probability of x is p s over x over p s given x, not times. I don't know why I thought that. Okay, then we can simplify s and x is going to be again some number t over k over x. So that's going to be tx over k for probability. Okay, so that would mean px is 50. That's going to be 50t over k, which is b, and then likewise for x is 80. That's going to be 80t because it's xt. So 80t over k for c. Okay, so that means then it's a bit tricky to spot what's going to happen here. But we can solve for k, so we can say that k, no, or t. I think t might be nicer to solve. T is going to be 1 over 50. So 50t is equal to kb. So t will be equal to a fifth. So then that means, therefore, 80 lots of t. So 80 of 1 over 50 kb over k is equal to c. Okay. And that, I'm going to bear that in mind. So therefore, if I simplify it, c, well, 80 over 50, and then the k's cancel. So it's going to be 8 over 50, which is 8 over 5b. There we go. Okay, that's the proper way of doing it. There we go. Can't rearrange, apparently. God. I've done all these math videos now, and now I've just fumbled here. Oh my God, how embarrassing. Okay, now the approach is the same. So we've done that. So part B, is it now? I think it's part B, yeah. So again, probably x is 20. That's going to be tx. So that's going to be 20t over k, which is a. Therefore, a, we're going to substitute t in. So remember, t was 20 of 1 over 50 kb over k. So that's going to be 2/5 b. Okay, because 20 over 50 would go to 2/5. K will cancel, and you're left with b. Okay, then probably x is 100. Now it's going to be 100t over k, which is going to equal and that's going to equal d, right? So therefore d is going to be 100 of 1 over 50 kb over k, and that's going to equal, again, the k's will cancel, and so you're left with 100 over 50, which should be 2b. That's okay. So that's a new probability. So now this will change up here, 8 over 5. This will now be 2b, and that'll be 2/5 a. So it just flipped. Okay. So then we can add it all together to say 2/5 b, add 8 over 5, add 2b is 1. So then we add that together. 2/5 add 1, add 8 over 5, add 2, gets us 5b. So b is the fifth. That's a bit nicer. There we are. So then if you complete the table filling in these values, b is simply a fifth. A then is 2/5 of b. So that's going to give us 2/5. 2/5 times a fifth. That will get us 2 over 25. And actually, I could have checked my answer was wrong as well. If we added up the probabilities, and this probably would have added up to 1. If they don't add up to 1, then something go wrong there. So then I would have checked my answer. But yeah. Oh my God, I can't believe that. I just rearranged. Anyway, So then 80, I'm sure a lot of people screaming now, like, oh my god, why it takes so long to rearrange? You rearrange, you rearranged it wrong. And then I went through all of that, where you all screaming, like, oh my god, you made a mistake. We got there in the end. Anyway, 80. So then that's going to be 8 over 5. So it's 8/5 of a fifth. That's going to go to 8 over 25. And then D is going to go to 2B. So that's going to be 2 lots of a fifth. That's going to be 2/5. Okay. And there we are. Got there in the end. Great. Oh my god. Okay, then what's part C saying? Nav tries a larger number of times to throw the ball into a cup from a distance of 100. He successfully gets the ball in the cup 30% of the time. Okay. State given a reason why T-Sam's model is not suitable. Okay, so for all values of x. Okay, so there's going to be some values of x then that we try from here. So, oh god. So one of these 4 values here is not going to give us a sensible answer, most likely. That's which one we're going to test. We could test them all. Let's have a look. Now, so throw a couple 100 centimeters. So in particular, x is going to be 100, I think. So he successfully gets the ball in the cup 30% of the time. Right. Okay. So what that's saying is, this is saying the probability of S given X is 100, isn't it? So the probability is successful, given that he has a distance of 100, that's 0.3. But we know what S given X is, don't we? S given X is this expression here, K over X. So that means K over 100, so X to 100 is 0.3. Therefore, K is going to be 130, right? But then it said for all values of X. So we want to then try other values of X other than 100. But we know what K is now. So we know what KX is. No, K. So K over X will become 30 over X, wasn't it? So then let's try some values, because that's what it asks us to do, for all values of x. So let's consider x is 20 first of all. So then 30 over x will become 30 over 20, which would be 3 over 2, which would be 1.5. Ah, hang on a minute, what's wrong there? Well, that is a probability that's bigger than 1. That defies probability law. It has to be below 1. So what I'm going to set for only 1 mark, really, even if you have to solve some at first. So what I'm going to say is actually K is 30 when probability of S given X is 100 equals 0.3. But when K is 30, probability of S given X is 20, which is A. That's going to be 30 over 20 equals 1.5. And which cannot happen, as a probability must be at most 1, right? So therefore, Tissam's model is not appropriate here. Okay, there we are. Okay, oh god, got there in the end. Okay, so that is the general strategy, though. Obviously, make sure you can rearrange. Oh my god. But that's the strategy with these sort of probability distribution table questions, which I see come up often. You may most of the time you get to work with and just try out the probabilities to see what happens, which is what I've done here, right? So I had to do a bit of work to get P of X first of all by just rearranging the conditional probability formula. By the way, general, if you have probability of A given B, that's the probability of A and B, and it's given B, so that's the outer probability B. That's the formula you need to learn anyway in general for conditional probability. Um, but it makes sense in my opinion anyway because it's saying given B, so B has to happen, so the total is B. So the probability of B, that's your total. Then if it's A given B, so it has to be A but also B at the same time because it has to satisfy B as well. So it has to be out of A and B, out of probability of B. I don't know. That makes sense in my view anyway. But then make sure you rearrange it properly. Oh god, I did all the probably in the harder math bit, and then I just got to rearrange the formula. Okay, but that's a strategy, right? Just substitute the values in, play around with it, then see what values you get, and eventually at the end, it all came together, and they could solve it. And also note they have to equal one, so you're probably gonna have to solve something equal to one, like we just did there. Okay, it's quite a nasty question, but hopefully we've gone over it now. You get the whole idea. I got one more probability question. So it says a medical researcher studying the number of hours a patient stays in a hospital following an operation. The histogram on the page after it summarizes the results from a random sample of 90. I'm going to highlight that. Using histogram to estimate P of 10 and 30. So we're given histogram here. So P of 10 less than T less than 30. So what that's going to be, with a histogram, but the only thing you know of a histogram really is the frequency is the area of a bar. But that's going to be helpful because if we know the frequency of everything, that tells us the total, but the total we know is going to be 90, but that won't help. So then the probability between 10 and 30 is the same as the proportion between 10 and 30. So therefore we have to just work out the frequency specifically of the bars between 10 and 30 there. So it's just a simple area of a rectangle question. So the total's out of 90. I'll bear that in mind. But first of all, we're going to do the area of all these bars. So this has a width of 2.5. It's going from 10, and this will be 2.5 there, and then there's a height of 4 for the frequency density. So it's going to be 2.5 times 4. This is basically like a GCSE question, really. And then the next bar, this whole bar here, that's simply going to be 2.5 again for the width. And also that's 12.5, sorry, not two. The width is 2.5, but that's 12.5. Anyway, so then another 2.5 for the width. No. This is 16. Oh god, they're really naughty at Edexcel. That's 16. That ends at 16, not 15, so it's 3.5. So from 12.5. No, now that's 12. No, this value here is 12, not 12.5. So then let me see this again. So that's 10. That's 10.5, 11, 11, 12. Okay. Oh my god. So that's 2 times 4. So the width of 2 and then the height of 4. So that's 2. Then this width is 4. I'm just going to do the width first. That's 4 from 12 to 16. Then that goes from 16 to 20. That's nice. Look at 4. And then the width here from 12 to 30 is 10. Okay. So the width then is going to be 4 here. So we're working from the bar 12 to 16. And then a height of... no, the height here is going to be 4 point... What's this here? That's going to be 4.2. Okay, if you can interpret what the scale of the boxes are. So that's going to be 4.2 here. So that's the height of the width of 2, and then the width of the next bar is 4, and then a height of 4 as well. And then the next one here is going to be a width of 4 and a height of 3.5. And then we're also going to have this final bar here with a width of 10 and a height of 1. And that's all going to be out of a proportion of 96. And then if we put that in the calculator, we should get the probability is uh oh, it's a weird one. You get 121 out of 240. Is that right? I wouldn't be surprised if that was wrong, given all the other mistakes I made. Uh, yeah, what have I done here? 2 times 2 times 4.2, 4 by 4, 10 times 4. Oh, it's not out of 96, it's out of 90. Where did I get 96 from? Oh my. Oh, it said I wrote 90. It looked like a 6. My bad handwriting. Oh my god. I need a break. I think it's clear because I was also I'm not to like give excuses, but I literally just did the mechanics paper before this that I uploaded, so I'm a little bit out of it. But you know, I'm a little bit tired. But we power through it. Anyway, we corrected ourselves there, and there we are. I couldn't read basically. Okay, so that's part A. Cool. So hopefully you know how to work with a histogram. There we are. For these 90 patients, the time spent in the hospital had a mean of 14.9, standard deviation of 9.3. Thomas suggests that T can be modelled by N. State with reference to a histogram whether or not his model could be suitable. So we have to look at the histogram. It's saying it can be approximated by normal. Um, but a normal curve is going to look like this, isn't it? We can kind of do the same sort of thing here if we kind of just like plot kind of like all the points on the bars. And I guess it would look like this. But obviously, you can see the curve formed by the histogram. It, it's not. It's not looking like a normal because the whole point of a normal is about the mean in the middle of the hump. It's symmetrical either side. Clearly, it's not symmetrical. As you can see there. And you can kind of see that here because, for example, this bar, say this is clearly going to be the mean, right? The highest value, the peak, somewhere there. But then when it dips here, and then it dips here on this bar, clearly this bar has less of a gap than here, so it's not symmetrical. And that's going to be our answer essentially. So part B, a normal not symmetrical. The histogram is not symmetrical. So a normal uh, distribution is not suitable here. Okay, and again, like if you plot roughly the points on the histogram, like we just did, it would be a symmetrical smooth curve, right? So it would be a suitable uh, guess there. Anyway, cool. So there we are. And they do like asking that from time to time. Why can't you use a normal distribution? is going to refer to the fact it has to be symmetrical. And usually data, I mean, it's not always symmetrical, so yeah, just bear that in mind. Chang suggests that the frequency polygon based on the histogram could be modelled by the curve of equation. So that's what I drew there, like the frequency polygon. So like the frequency polygon, like the midpoint of like all the gaps. And he's saying basically the curve, instead of a normal curve, the frequency polygon, if you draw like the midpoints of the bars at the top, is now going to be this instead. So this is not a normal, it's going to be this equation, which should be more reflective of the data and the distribution of the data. Anyway, that's just a bit of the backstory here. But we're given the curve, don't have to worry about where it came from, really. And we're given x is measured in tens of hours, in bold, interesting, and k is a constant. Use algebraic integration to show this. So we don't need any stats here. We just need some integration. So we're going to integrate between n and 0. What was it of k? Oh, no k in there. It was xn. What was it? No, would it be x to the n? No, it would be x e to the minus x. That'd be a really difficult integral. X e to the minus x dx. And what you're going to notice is how we're going to evaluate that. It's going to be by parts, isn't it? Which is also why I say do not forget your pure knowledge if you do applied. You know, they can bring up any part really of the pure spec in the applied paper. And I remember when this paper came out in 2023, loads of people after SATS exam like, oh my god, what's this integration doing here? Why do we have to do by parts? They can get you to do that, so just be prepared. But actually, they do give you integration by parts in the formula book, but you need it's given here in the integration section, but you need to recognize that's by parts because it doesn't tell you it's by parts; it just gives you this. But so I'm going to jot that down. So I'm going to say, well, the integral of u dv dx is going to be equal to uv minus the integral of du dx v dx, right? Is that it? UV minus V du. Okay, it's the other way around. It doesn't really matter. It's the same thing. Okay, so what we need to pick then, we need to pick a U and a V. So here we have a U and a dV. So U is going to equal something, and dV, dx is going to equal something. So what are we going to pick? And in order to differentiate, you're going to use the layout rule here. And what I like to remember is actually dilate. You don't need to use the I bit for an all A level. So this stands for logs inverse trig. That stands for algebra. So like polynomial terms like x squared, x to the 4, x, and so on. That's a trig function, and that's an exponential function like e to the x. So that tells you the order to pick your differentiation. So you what you're going to want to differentiate. So that's going to be your u value, isn't it? Because your u you're going to want to differentiate. And then di, the di stands for differentiate. So what you're going to differentiate and which function this is late. You don't need the I because you don't deal with inverse trig with integration at A level, in the normal A level anyway. So I like to remember this dilate. So what we're going to pick differentiate, well, which one comes first? L, there's no logs, there's no inverse. A, we have an algebra term, so we have an x. So we're going to want to differentiate x. So that's going to be u, which will then go to 1, because x will go to 1. And that makes sense, because then if we differentiate to a constant, we're going to be left with some form of e to the minus x. We know how to integrate e to the minus x. But anyway, that'll go to e to the minus x then, by default, the other function. And then we integrate that. Well, it's going to be minus e to the minus x, isn't it? And then we're going to plug that into the by parts formula. So therefore, the integral of x e to the minus x between n and 0. well, first of all, let's just integrate. So uv is going to be x e to the minus x minus the integral of du, which is going to be 1 times v, which is e to the minus x dx. And that's all going to, because we're integrating between n and 0, that's all going to be between n and 0. So that's going to be x e to the minus x. Then it's going to be plus e to the minus x. And again, that's going to be another integral. So integral of e to the minus x again is minus e to the minus x. Because that's what we got there. Might take the minus out, you get minus of a minus, you get positive. Positive e to the minus x, integrate that, you get minus e to the minus x again. So that will all go to minus e to the minus x between n and 0. And so then we just plug the limits in. So that's going to be n e to the minus n minus e to the minus n minus 0 e to the minus 0 minus e to the minus 0. So that's going to be n e to the minus n minus e to the minus n. And so that then we got a minus, and then we've got a 0 here, so let's go to 0. And then e to the minus 0, so e to the minus 0, but e to the 0. E to the 0, or anything to the 0, is just 1. So we're going to left with minus 1, but then it'd be a plus, minus of a minus with plus 1. Then I think we can factorize this a little bit, can't we? Then we can say it's e to the minus n of n minus 1, add 1. What did they want us to show? It's 1 minus n plus 1 e to the minus n. Okay. So we need to say 1, and then we need to factor a minus out. So e to the minus n. Then if we factor a minus out, instead of n minus 1, it was simply 1 minus n. Is that what they wanted? I feel like I made a mistake here. N plus 1. What have I done now? What do I get? Oh my god. Oh, uv. That's why. uv here is minus e to the minus x. Because v is minus. My apologies. So that's minus. Easily rectified though. So that'd be minus n e to the x minus of minus. I could have just factored the minus out, couldn't I, really? But oh well, we're here now. So that'd be minus e to the minus n plus 1. So that'll go to e to the minus n. I could factor a minus out, so that'd be n plus 1. So that'd be left with 1 minus e to the n. There we go, n plus 1. There we go, got there in the end. Okay, bloody negatives. I made all the classic mistakes. I misread a number, I misread a negative sign. I rearranged the basic fraction. I made all the classic mistakes. Oh my god. There we go, showed it there. And then we show that for Chang's model, case 99. Okay, so what you then need to remember that this again represents the histogram, the frequency polygon, which would be basically the histogram shape, essentially. And so if we imagine then the area under this frequency polygon, something like this, right? Again, the area has to be the frequency because it's the area under a histogram, right? Because that's what the curve is reflecting, essentially, the histogram. So the area has to equal, the total area has to be 90. So we have to work with our limits then. Well, we know it goes between 0 and 4 for x. So really, the whole area is going to be between 0 and n is 4, isn't it? To give us the total area under the curve. And the total area is the total frequency of 90. So therefore, we can say, was it part C now? We're on part D? I can't remember. So the integral of, I think it's part D. The integral between 4 and 0, because that's the limits of x, 0, x, and 4. the total area of, and also because x is in tens or thousands, it's between 0 and 40. And we know that the time goes to 40, so it is the area of the whole histogram. Okay, because x is 10t essentially. Anyway, so it's between 4 and 0 of x k x k x e to the minus x. Why is that? Because we are integrating. Oh, wrong question. We are integrating the curve. So we integrate k to the minus x, but we know what x e to the minus x is, so we just need to add a k on. Okay. And so that will have to give us 90, right? The whole area under the curve. But we know what the integral of xc is. So k, if we bring a k out, that's going to be k of integral of that by 4 and 0. We know from the other, what we just did, what the expression is in terms of n. So if we plug in n is 4 now for our upper limit, so that's going to be k lots of 1 minus e to the minus 4 of 5, n plus 4 add 1 is 5. That has to equal 90. Therefore, k is going to be 90 over 1 minus 5 e to the minus 4. And so it said, I think give it to one decimal place, was it? So, or nearest integer, I can't remember. But it was 90. So put that into calculator. You get 90 of 1 minus 5e to the minus 4. And we get 99.029. And so that's 99 to nearest integer. And I think that's what they wanted, right? Yes, k is 99 to the nearest integer. Cool. Okay, then it says estimate p of 10 between 10 and 30 using Thomas's model. I don't know whether I'm supposed to use it again when we've already shown why you shouldn't use it. But anyway, estimate the probability using Thomas's model. Do I have enough room up here to do it? I think I do. I'm going to do it up here instead. So I don't want to keep scrolling down. So part E then. So I. So Thomas's model. So simply T between probability. Sorry. Of 10 of T of 30, and we're given the normal distribution of n of 14.9, 9.3 squared. We have to move. There we are. So between 10 and T and 30, but that's just calculator work. So again, let's go to our calculator. Let's go to 7. Then let's go to, well, it's a cumulative one, so it's going to be normal CD. The lower limit's 10. Again, because it says less than, we can also say less than or equal to. With a normal distribution, when it equals a number, the probability is 0, so it doesn't matter if you have less than or less than or equal to. Okay, so we just put the lower as 10 and the upper limit as 30 with a mean of 9.3. Okay, not 9.3 squared, 9.3. That's the standard deviation. And the mean is 14.9. And so we should get this answer of 0.64 863. I'm just going to say 86. That should be fine. And then part 2 is then estimate the same probability using the curve. And so the probability again. So basically, you need to realise that this is given essentially the frequency under the histogram. That's not the probability. So what we're going to, so between 0, 10 and 30, we're going to want to integrate between 10 and 30 because x is tens of hours. So x is going to be 1 at 10 and x is going to be 30 at 3 at 30. Okay. So we're getting into the integrate between 3 and 1 of k, or 99, x e to the minus x dx. But the problem is we're only going between n and 0. So actually we can alternatively say this is the same integral between 3 and 0 of 99 x e to the minus x minus the integral between 1 and 0, okay? Because then that would give us strictly the area between 3 and 1. Hopefully you can see that, right? So that's going to be integral of, if I do that down here, minus the integral of 1 and 0 of 99x e to the minus x dx. So then now we can choose to plug those values in the formula. So it's going to be 1 minus, well, we can factor a 99 out first of all because it's just k is a multiple 99 of, then it's going to be using this formula. So n is 3 first of all. So it's going to be 1 minus 3 add 1. So it's going to be 1 minus 4 e to the minus 3. And we're going to be taking away when we plug in n is 1 for the second integral, and we're going to take that away, so it's going to be minus 1 minus minus n plus 1, so it's going to be add 1 add 1, which is 2, e to the minus 1. And so if we compute that in the calculator, we're going to get the result. So 99 lots of 1 minus 4 e to the minus 3 minus 1, add 2 e to the minus 1. So we should get an answer of 53.124, okay, which makes sense. I guess it's a fairly sensible frequency. I'm going to get rid of this now. But that'll tell you the frequency between 10 and 30 here, right? So between 10 and 30 here, using the curve. So then that's how many are between 10 and 30. So to work out the probability, again, that's going to be the proportion that's between 10 and 30. So therefore, the probability between 10 and 30 is going to be this 53.124 out of the total 90. And so that would be 0.5903. Okay. Yes, that's right. There we go. Cool. And yeah, that's it. So hopefully you reckon. I think that's probably the hard. I think this really tests his skills. Hopefully you can I can reckon that these are probably quite difficult. Hopefully you recognise that this area, this integral, is given the frequency between those parts here, like a histogram. It's given the frequency, not the probability, between like 10 and 30. Okay, so then to work out the probability, you've got the frequency between 10 and 30 out of the total 90. That would give you the probability. Okay, final question. The researcher decides to use Chang's model to model probability between A, T, and B. State one limitation. Okay, what I notice is A and B are not specified. It just says A and B. Well, actually, the limitation, and again, the limitations usually consider the larger values of the model, so larger values of t in this instance. So Chang's model again here. So what would happen if x is bigger than 4? Then um, then we wouldn't get a suitable model, would we? So that's the limitation. You can't predict it for values larger than 4. And remember, the 4 corresponds to people who wait more than 10 hours. So what he's saying that what we're saying essentially is you cannot extrapolate the model for values larger than 4. So values when patients spend longer than 40 hours waiting. No, sorry, the time spent in the hospital in the operation. Sorry. So you cannot extrapolate it. Essentially, is what it's saying. So the limitation is you cannot use the model for values larger than t equal to 40, essentially. And that's really it. So t for the 40 hours, I guess you want to put it in context. Which that again, that's because as 0 is less than x less than equal to 4. Okay, that's when the model's valid for. So anything above that or outside that range, you cannot use the model. So that would be extrapolation. And you cannot use extrapolation here, or else you get inaccurate data. Okay, cool. And that's it. There we go. That's the stats part. Okay, I'm going to switch back to mechanics then, but I'm going to take a toilet break. But obviously, I'll probably edit that out so you wouldn't see that. But then we're going to look at mechanics. And this is from October 2021. Okay, so yeah, I'll be back in a sec. Okay. 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 I think back up or break. Okay, we're gonna go on to mechanics now. And this was again taken from October 2021. If you want to look at it. And yeah, I picked that because I think it had some slight nuances and differences to the other mechanics paper, which I think I want to go over. But you'll see it's mostly the same. So let's have a look then. So question one: a particle in P moves with constant acceleration. If you see constant acceleration, you're gonna have to remember Suvet, right? Suvet only works with constant acceleration. So then at time t0, P is moving with velocity 4I. Find the velocity at time t2. So again, Suvet S, we do not know anything about. U, we know initially it's velocity of 4I, so it's going to be 40 in a column vector form. V, we're trying to work out. A is 2 minus 3, that's in column form, 2I minus 3J, and T is 2. So actually we've got all the ingredients to work out V. So we need an equation from Suvet that does not have S in it. And actually it's this one here, V equals U plus AT. That's if you hadn't remembered them, but yeah, so V equals U plus AT. So then V is U, which is going to be 40, U plus 8, and 2 lots of A, which is 2 minus 3. And then we do all that as a vector, and we do vector addition, sorry, to bring it to one vector. So 4 add 2 lots of 2 is going to get us 8. The top one, and then 0 add 2 lots of minus 3 is just going to be minus 6, and that is going to be simply your vector at t is 2. So just use Suvet there because we have constant acceleration. Cool. And then part B says, what does it say? At time t is 0, the position vector relative to a fixed origin is I plus j. Find the position vector at time t is 3. Okay. So first of all, we have to do some displacement. So that's going to be S. We're going to want U. Again, we know it's 40. V. We don't know V because V here is at time t is 2. But we want t3, so that wouldn't be the velocity, so we wouldn't know that. A again is constant 2 minus 3. And t would now be 3. So now we're going to look at the formula book and see which one of the Suvet equations does not have V in it. Let's have a look. Here we are. So it's the second one. S is ut equals a half AT squared. Let's have a look at that. So S is ut and a half AT squared. So therefore S, the vector, is going to be ut. So that's going to be 3 lots of 40 and a half of A, t, so t squared. T squared is 3 squared, which is 9. So 9 over 2 lots of A, which is 2 minus 3. And then we do that, we get the vector S is 3 lots of 4 and 9 over 2 lots of 2. So then we get 21 on the top. And then 3 lots of zeros is 0. And then 9 over 2 lots of minus 3. So 9 over 2 times minus 3 will get us minus 27 over 2. Okay, now what you actually need to realise, and actually it's quite nasty though you do this for 2 marks, because it might trick you. But this S that we worked out with constant acceleration, that is not the position vector. Okay, it's asking for the position vector at time is 3. What we worked out there is the displacement done, or the distance, or whatever, the displacement done between those 3 seconds. Okay, so in other words, if we started at A and then at T3, it's at B. What we worked out there is between these 3 seconds, that displacement vector of, what was it? 21 minus 27 over 2. Let me have a look at that. Yes. What we worked, that is AB. Okay, that is the direction, the vector between A to B. That is not a position vector. What we then need to do is to find the position vector of B. What you need to do is then consider, well, again, like with normal mass vectors, where we have an origin to have a position vector. If we want to find O to B, you can alternatively go from O to A and then A to B. O to A, they told us, is I plus J. That's the position vector at time is 0. So you're going to want to then add O to A and then A to B, essentially. So the point at A is T0 and the point at B where T is 3, okay? So that is what that S is doing. That S finds the displacement, the vector between 2 points, not a position vector. To work out the position vector, you need to do this sort of method, okay? By adding a point O and then, doing your vector triangle. So, therefore, O to B, or, I don't know, the position vector, I'd say, because it didn't tell us the point. So the position vector at T is 3. That's going to be the original position, which is I and J, so it's going to be 1, 1. Add our, then if we go to O to A, and then we go from A to B. So A to B is this displacement vector of 21 and a minus 27 over 2. So then you need to compute that. Well, that's going to be 22, and then 1 minus 27 over 2. And that's minus 25 over 2. And so that is your position vector. So that's how with constant acceleration, you can work out a position vector at a point given the displacement between 2 points, okay? So to reiterate, this S with constant acceleration with vectors gives you the displacement, the vector between 2 points, and not a position vector, not a single point, okay? You might think it will give you the position vector after 3 seconds. That's not what's going on there, okay? But when you have variable acceleration, this is where it gets even trickier. With variable acceleration, when you obviously integrate to get to displacement, that will give you the position vector. So it works the other way around. But that's something I think that's probably the hardest bit with vectors, is realizing which displacement gives you the direction and which displacement gives you a position vector. So with variable acceleration, you integrate, do calculus, you get the position vector straight away. But with SUVAT, with constant acceleration, then if you use the SUVAT way, it will give you the direction vector instead. So then you need to do this sort of thing. We'll go from O to A and then go along the displacement to get to the position vector. Okay, hopefully that's clarified. Question 2. So we're given a small stone A of mass 3m, touch the one end. So it's a pulleys question, right? Again, with these sort of things, you need to label all your forces. So it's a rough plane. So we're gonna have friction either this side or that side, but also we're gonna have mass, aren't we? Either side. B is gonna have a weight, not mass. Sorry, weight. Well, have a mass obviously, but have a weight of mg. Because remember, weight is mass times g, the gravity constant. G is 9.8. That's gonna be mg. A is gonna be 3g, 3mg. And remember, because this is inclined, it's best to do it perpendicular and parallel with an angle alpha there. So that's going to be 3m cos alpha. And that's going to be 3mg, sorry, sine alpha. So that's the component parallel and perpendicular to the plane. I realise this is sine quickly because it's facing the angle. So it's going to be sine. Okay. Actually, I'm going to make this a bit clearer, sorry. There we are. So we're going to have this, obviously, the mass acting the weight acting straight down. So then that's going straight down. So this component and then there, that's alpha. That's going to be 3 mg cos alpha, and that's 3 mg sine alpha. There you go. Hopefully it's a bit clearer to see. Okay. I still is a bit messy in it. I don't know. We'll live. But it's also going to have a friction. It's also going to have a reaction force, isn't it? So it's going to have a reaction force of R. And B, and also there's going to be tension, isn't there? Along the string. Um, and tension will act towards the pulley in both of them. So T here and T here. Why is the T equal? Because essentially it's what does it say about the string? It doesn't say anything about the string here, but they always will be equal if connected particles like that. It doesn't say anything about the string, but usually the tensions will be equal because they're in a connected system. Um, but yeah, so that's the assumption. Again, with connected particle situations like this with a pulley, you just need to recognise that. And they're also going to be acting towards the pulley as well. And I guess you can see that because the pulley itself isn't going to have any, it's not going to move anywhere. The pulley will stay where it is. So then the tensions have to go towards each other to cancel each other out. If we had the tension going here and then the tension going there, it's going to probably move the pulley, but we don't want to happen. We want the pulley to be fixed. So then if we counteract each other, the tensions going facing each other, so they kind of cancel each other out. Basically, all the pulley's fixed where it is. If that makes any sense, rather than the tension being passed through the pulley and then down the slope. I don't know if that makes any sense, but that's the theory there. At least how I remember it anyway. I don't know how correct that is, but I don't know. But the tension will act in that sort of way. But now we just need to work out where the friction's going to go. So we need to know where A is going because friction will always oppose the motion. But we need to know where the motion is for that to happen. Where does it say? Stone A is released from rest and begins to move down the plane. Okay, so if it's moving down the plane, the friction is going to go the opposite way, upwards. So there's also going to be a friction part here. Okay, so there's two forces. So there we are. And that's all our forces. Also, mu is 6. And we know that tan alpha is 3/4. So that's all the information. We added all the forces. That's the hard part done. And the string, light and inextensible. There we go. So that's also why the string will be equal on either side. But there is a question about that at the end. We'll go on to that later on. But anyway, so again, once you've got all the equations, it's best to just write everything down. So not the equations. When we label all the forces, we're gonna have to use them. They're not gonna give us all this question and then not ask us to do anything with the forces. We're gonna have to resolve essentially. So let's just resolve before we look at the question. Okay. And often than not, you probably end up answering the question anyway by doing that. So when we resolve, because we've got two particles and they're connected together, usually because of a pulley, you can consider them separately. So let's consider A first of all. So particle A, and then we're going to do the normal thing. So at A, first we need to resolve perpendicular to the slope. So that's going to be firstly R, but then R is going to equal the 3 mg cos alpha, the weight component that's perpendicular. So for R is equal to 3 mg cos theta. That's great because actually we can find alpha as well. So we can get an answer for R. And then let's do parallel to the slope. So R are parallel. And that's going to be, well, F and T are going that way, and then the 3mg sine alpha, the weight parallel, is acting the other way. So F and T minus 3mg sine alpha. Now why did I could have put equal to, but I can't. Why not? Because it's actually saying it's moving. Stone A is moving down the plane. That means it can have acceleration. Because of that, because all these resolving is essentially using F is MA. That's how we get it. But when the acceleration is 0, simply the forces opposite sides equal each other, which is what we've done here. But when it's perpendicular to the plane, uh, there's no movement perpendicular. The only movement is up and down the plane, so the parallel component. So in this case, when we're going parallel, it's going to equal MA. This is the resultant force, and that's going to equal MA. Okay. So that's not going to equal 0. It's going to equal MA. So hopefully you bear in mind because it's moving down the slope. And actually, I guess what we should have done, actually, we should have resolved downwards because that's where acceleration is. But it won't matter because acceleration will just be negative after this. You know what? I'm going to leave it as it is and then demonstrate it because then we can just flip the sign because acceleration will not be going upwards, the slope, it will be going downwards. But we'll deal with that in a minute. So that's our two equations. But we also know that F is mu r. So the friction is mu r, where mu is a sixth. Okay. And we also know at B, we can also, and then at B, we can do the same sort of thing. We can resolve up and down, left or right. So we go up and down. So if we resolve upwards, that's where the acceleration is going to be for B. That's where B is going to be moving, right? It's going to move upwards because when A essentially going down, it's pulling the rope to move B up. If that makes any sense. So it's going to be going up, so that'd be the positive direction. But again, it won't matter. But B, so the tension is going to equal mg essentially. So if we resolve upwards, T is going to well, no, sorry, T minus mg is going to equal ma. And actually, I should say, A has a mass of 3m. So actually, this is not ma here. This is 3ma. But B has a mass of m, so it's simply ma. But then we could resolve right and left. But at B specifically, there are no left and right forces, so there's nothing going on there. So those are all the equations we can deduce, right? When you've got an equation over a pulley, a situation, that's what you do, right? That's how you essentially go about it. So now we just got to do all of these, right? And so let's look at the question. Write down an equation of motion for A. So equation of motion basically means you have to relate it to, well, either velocity, acceleration, or displacement. But the only thing we've got is acceleration. So we're going to have to deal with this equation here. So the equation of motion, we're going to be interested in particularly F plus T minus 3mg sine alpha equals 3ma. And that would be fine, actually. That's your equation of motion. And then it says for 7 marks, show that acceleration of A is a 10th g. So we need to find A. And that's 7 marks, so obviously you're going to have to solve it all essentially. Okay, so that's part A. Then part B. Well, we're going to solve it. It's like, again, it's just boiled down to simultaneous equations. We've got like 4 different equations going on. Let's work with it. So this is complicated. We don't know F, T, or A, so I'm going to leave that where it is. But I recognise that firstly this bit here, T minus mg is equal to ma, but then T simply m, a, and mg. So that would help for this equation at the end in part A. Okay, so that's cool. So I'm going to highlight that. Then I'll notice F is a sixth R, but I also know that R is up here. R is 3mg cos alpha. Now, cos alpha we can actually evaluate because we know that tan alpha is 3/4. And so what we can do is realise if we then construct a triangle with alpha, as so, a right angle, alpha there. So it's saying if we use SOHCAHTOA, TOA, so opposite over adjacent, so the opposite is going to be 3 and the adjacent 4. If we then did Pythagoras to work out the hypotenuse, it'd be at 5. Okay, so square root of 3 squared and 4 squared, that will give you 5. Okay, so therefore we could say from this sine alpha is opposite over hypotenuse, so it's going to be 3/5, and cos alpha is going to be 4/5. Which means R then is going to be 3mg times 4/5. So at 3 times 4/5, it's going to get us 12/15. And 12/5, sorry, mg. Now we got that as well. Cool. Okay, now we know that F is a sixth of R as well. So F is a sixth of R. That's going to equal a sixth of that, really. A sixth of 12/5 mg. So that's going to be times all that by 6. You get 2/5 mg. And there we go, we've got F as well, just in terms of m and g. That's fine. M and g are just constants, really, that we know. And yeah, that's it. Now we know F and T in terms of A, M, and G. We can now go back to our equation and A. So therefore, F plus T minus 3mg sine alpha is equal to MA, right? 3MA, isn't it? Yes. Right, okay. But we know F is 2/5 mg and T was MA at mg. Minus 3mg sine alpha. Now sine alpha again is 3/5. So 3/5 times 3 is going to be 9/5 mg equals 3MA. Now immediately I notice I can cancel the m's out because m is in everything. So therefore I could say 2/5 g add a add g minus 9/5 g is equal to 3a. And then I can move the a to the other side to say 2 of a is going to equal 2/5 of g add another g minus 9/5 of g to get minus 2/5. And that's about the negative we talked about earlier. I was expecting the negative. So that means A is simply going to be 2/5 divided by 2. You get minus a fifth G. Ah, okay. What's going on here? We should have a 10th G. Do you know why? Because the negatives do matter here. And again, this is a good learning curve. Because what I said here is that essentially at B, the acceleration is here, A. The acceleration is the same, by the way, for A and B. That's, again, part of the idea that they're connected particles. But what I said here is, I assumed A worked that way. That's fine. If we were just working with A, because then we get a negative. However, I kind of realised what was going to happen, but I did this intentionally, in a way, to show that this would fail, and why this is important to go over. So acceleration is working that way down the slope. Now, if we assumed it's the other way around, like I did, that would be fine if it was on its own. But then um, B has the same value of A. What I said here was, the acceleration is working that way and I called that A. But in theory, it would be the negative. But B is now in the correct direction for A, but I called it the same value. So one A is going positive or one value is going negative. That doesn't really match up because we've got two different particles. So we have to make sure in this instance when they're connected that you use the right value of A, okay, both sides. So in this particular case, we're going to have to go down the slope here at A. And then B would be going up at A. So the way to correct this is actually flip the sign. So instead of 3MA for A, I'm going to say it's minus 3MA. Because A, I'm going to make it minus A. And it should work out, hopefully. So therefore, that's going to equal minus 3MA. So that's minus 3MA. And that would be minus 3A. So then if I add another, so if I add the 3A, that'd be 4 of A, which works out. Is 2/5 of G, oh, and gone. 2/5 mg, add MA, add mg. So 4 of A is minus 2/5. So then A would be minus 2 over 5 divided by 4. You get a tenth. So that's what they wanted, but you get a negative. And that's what's expected, right? Because we assumed A for because the acceleration at A, we assumed it went up, but then we took the negative A to reverse it. So we say negative A is the positive direction for A. So then positive A would be negative, so we'd have to undo it. Okay, if that makes any sense. So therefore A is 1 over 10g going down the slope. Okay. As minus 10g is going up the slope, which is not what's happening, it's going down. Alternatively, you could save all the headache and just resolve, particularly in the, so when we resolve down the slope, we don't go up the slope, we want to resolve down, it, so we're facing the positive direction of A. And so therefore it would be 3mg sine alpha would then equal minus f minus t will get us 3MA, and we don't need to make a negative. But yeah, that's how you can save the headache. But you get a tech for G. Cool. Okay. So we got acceleration then. That's B37 marker. Part C. Sketch the velocity time graph of the motion of B from the instant when A is released from rest to the instant just before B reaches the pulley. Explaining your answer. So we want the velocity of B from the instant A is released to when, oh, I need to stop moving, to when just before B reaches the pulley. So obviously what's happening is, as I said before, when A is moving down the slope, it's pulling B higher up towards the pulley. Eventually then it will hit the pulley. So you want this velocity, what happens to be with the velocity as that happens. However, the only thing we know is acceleration, and actually B is moving up. Okay, so it will move up and the acceleration will go up. So what happens then? Because we know you only know acceleration, but we know the acceleration is a tenth g for b, because it'd be for b as well. So it's a constant, isn't it? Acceleration is constant at b. So then that would mean, again, suppose you can then visualize that the acceleration of the velocity at b is going to be constant. No, sorry, no, velocity, well, yeah, no, the velocity will be linear, sorry, so then v would be a tenth gt add some other constant if we integrate it, right? So the velocity time graph would be a straight line, right? Now, initially b is at rest as well, so it's going to start here, and it's going to be a linear graph up there. Okay, it's going to just look like that for v and t. And the reason for that is, again, because the gradient represents acceleration, right, of a velocity time graph. Again, think about it as a differentiation. The gradient represents the derivative. You know that a is the derivative of v. The acceleration is the derivative of v. So this would be the graph because the gradient is constant as acceleration is constant. Okay, so if a constant acceleration like this of a tenth g, then the only way is for v to be a straight line graph. Okay, um, and in particular, the gradient would be a tenth g specifically, but I don't know what that much detail. But you can say it. So gradient equals a tenth g. Okay, and it starts from rest, so it'll go from the origin 0, 0. Okay. Because what's happening, and also to explain, because it actually doesn't say B starts at rest, but A does. But the reason is, if A starts at rest and B's moving up, it's only moving up because A's moving down. So if A's not moving at all, then B's also not going to move at all. Because again, the tension will balance out with mg until then A moves, and then we add acceleration on. So then, okay, I hope that made sense. But that would be the velocity time graph. Because this grade is constant, then it says in reality the string is not light. State how this would affect the working in part B. So that's kind of what I was alluding to before. And that's because the tension in the rope or in the pulley, I don't know what it is. What's it? A string. There we go. Not a rope. The tension in the string would not be equal at A and B. Okay. Uh, so I can explain that. Well, being light means it has no mass. So the string doesn't have mass. Uh, but then if it, so, I guess if it has no mass, then then it would be have the tension would be equal throughout the string. Because the string itself does not require like because if we had mass in the string and it was like I don't know uh the mass was like weirdly distributed throughout the string. So say if it wasn't a uniform mass or whatever, uh, then some parts of the string would be heavier than other parts of the string, even ignoring the fact we have particles on either end. Um, so um, there would be more or less tension to compensate for the different areas of mass. But because A and B are at the polar ends, basically the string it's inextensible, it's tight, it's at max tension. And so the tension will be evenly distributed that way. But then if the string itself in the middle of it has variable mass in between, then the tension will vary in between the tension. I don't know. That's just something you need to learn. I'm not a physics person. I'm not going to lie. But I'm just going to say about light. So the tension in the string will not be equal at A and B. And that's just one of the assumptions you need to know. I think there's a page of the textbook with a bunch of assumptions. Like, what does light mean? What does inextensible mean? What does a rod mean? What does a peg mean? What does a particle mean? You just have to learn them, unfortunately. But as you do more questions like this, you start to realise what the assumptions mean in terms of actual question problem solving. And in this case, the string is light is important to assume the tensions are equal. Okay. Part 3. We have a beam AB with mass M and length 2A. The beam rests in equilibrium with A on a rough horizontal ground and B against a smooth vertical wall. The beam is inclined to the horizontal with an angle alpha. The coefficient of friction is mu. The beam is modeled as a uniform rod. Okay, that it should always be uniform. So what that means is the beam itself has a mass. So it's kind of like a rod, where it's like a particle, so itself, so it has a mass in it along it. But then if we assume it's uniform, the mass is evenly distributed on the beam. So we can just assume the mass is halfway between, because then if it's evenly distributed, then either side of the rod is going to be equal and they balance each other out. Um, so then all the mass can essentially be assumed to be concentrated in the middle. Anyway, so then that's going to be A between A either side, and that's going to be mg, mass of M, so mg. But we're also probably going to have to resolve perpendicular parallels. That's theta. So that's going to be mg cos theta and mg sine theta. Cool. We also told stuff about A and B, and at A, it's on a ground, and the ground is rough. So what that means is there's going to be friction, isn't it? So where would the friction act? So friction at A, so it's going to be along the floor, isn't it? So it's either going to be that side or that side. But think about it, really. This is, if you kind of think this is like a ladder, it's going to want to slip to the left, isn't it? The movement's going to go to the left, and you can see that with the weight as well. So if the weight goes down here, it can go here and here. The no, sorry, no, because the weight's actually straight down. That wouldn't affect it. But at B, there would be a reaction force because it's a surface. So if we get rid of this, this will be perpendicular to the wall. So there'd be a reaction at B, but this is pushing the ladder then to the left. Okay, so to oppose that motion, we're going to have to have friction to the right. Okay, here. Okay, but there's also, because A is it's a surface, the rod touches the surface, there's also going to have another reaction at A. Okay, until that's A as well, the distance between A and B. So that's distance A, and that's distance A. Okay, cool. So I think that's all the labels for added. I think just to check, B's a wall, right? It's a smooth wall, so there's no friction. God, there's friction on both ends. I don't know, model that, I guess. But I guess the ladder would also be slipping downwards because that's what the mass is doing, right? Uh, the mass would pull the ladder down, so friction would have to go that way if there ever was a friction at B. But luckily, they're not usually that nasty. But yeah, so we label all the forces now. Um, So we can get resolving, can't we? And then again, like we did before, once you got the hardest bit is just labeling and resolving all the forces in like certain directions. Once you got the forces down, just write down the equation because you're probably going to need them. So before we do anything with the question, let's firstly resolve. And now, there's a lot of forces in this sort of question. That's just literally up or down. That's literally up or down or left or right. Okay. So it's best to, instead of resolving perpendicular and try to convert every component to be perpendicular and parallel, I think it's best to just go up and down in this particular case. So if we then firstly resolve up, and I need to note it's an equilibrium, so the forces will equal each other, the opposite forces, no MA. So if we go up, where you got the reaction force at A, and then we also have the weight mg. So that means Ra, the reaction force at A, is going to equal mg. Cool. Then if we resolve to the right, you can only go up or down or left or right. Those will be you can only resolve in two different directions. They're opposite each other. So then we go right and left. So friction is working to the right, but then the weight. Well, no, we already dealt with weight. But then we got the reaction force at B, haven't we? That's going the other way. So really, it's going to be F minus reaction at B, isn't it? So that means F is going to equal reaction at B. But there's another equation. Well, we also know really that F is mu R, and particularly R at A, because the friction obviously is acting at A, and A, the reaction force is RA. But we also know another thing, don't we, with this sort of question? We can take moments um, because we've got a rod or a beam. If you've got like a rod-like structure or a beam, so we got stuff acting all along the slope. But with the other question, the slope wasn't what we were interested in, it was the particles. So, for example, if we had like a slope question like we did before, we want to take moments here because it's just a single point. But now, because we have a line we're interested in rather than a single point, we take moments because the force is acting all along the line. Does that make sense? Because the beam is also like basically almost like another particle, but it's just a line. Okay, so it's going to be forces acting on that thing. But that was going to cause motion anti-clockwise and clockwise. That makes any sense? So that's why I consider moments here, not the other question. Because now we're dealing with forces on the line that's acting on the line rather than acting on a single particle or a single point. That makes sense? So we can also take moments. So I'm going to say then resolving anti-clockwise. At what point are we going to take it moments at? On the line, on AB, on the beam. Well, the most suitable choice is going to be the place with the most forces on it. So RA and F here at A, it makes the most sense to choose A because then that will get rid of forces to consider. And so then we're left with the weight part, the weight force midway, and then the reaction force at B. So then we're going to resolve at A. So then we need to consider what forces would make it anti-clockwise and clockwise. But another thing to note actually is because now we're dealing with the line, we need to consider with moments you have to consider the perpendicular distance. between A. So that's going to be along the line. You want the perpendicular. So if I have a line, we want the weight, for example, that's perpendicular. So that's going to be mg cos theta for the weight. What about our reaction at B? This is not a 90-degree angle. This is not 90 degree. So to make it perpendicular to the plane or the line, again, it's going to look like this, isn't it? If we draw it. It's going to go like that, and then therefore this component is perpendicular to the line AB. That's the component we're interested in. And then we can say we can also get a parallel component to connect RB there. So RB is going to act there. So then that will be a 90-degree angle because the parallel and the perpendicular component meet. So it'd be a 90-degree angle. So that's RB. But we need to work out this component here. So we're going to need an angle. And again, this is where we're going to have to be a bit smart. So we're going to consider Z angles again, aren't we? So we have this like the ground here, we have the slope here, which is theta. Then we're going to need to consider adding a line. Well, this here we have RB. RB is also completely horizontal, so it's going to be parallel to this line here, right? So we have a Z angle. If this is theta here, this is going to be theta as well. So this angle here is theta, okay? So what we have then is if we draw it here, we have theta here. Oh, we have theta here, and we also have this triangle here, which is what we want. That's 90. But we want to work. But we can work at this angle because if we draw it here, because this whole angle here, these two angles combined, this angle and the theta angle, add up to 90. So that's going to be 90 minus theta. That's a 90 degree there. It's corresponding to there. So this angle then is simply going to be 180. Take away the two angles because the angles in the triangle add up to 180. So this angle here, is going to be theta because 180 take away 90 is 90. Take away 90, take away theta. Right, you're just left with positive theta. So this angle here is theta as a result. Okay. So yeah, I think that's the tricky part of this sort of question is to know where your angle theta is going to be when you make a triangle. So then this is simply then going to be RB sine theta. Okay, and there we are. So that'll give us then the perpendicular component there, right? That's the perpendicular reaction force to the line. Okay, now we can take moments. So, so first of all, we already resolved the weight to be perpendicular. So mg cos theta. So where is that going to add? So if I draw a line, not a line, if I get a line out. Oh God. This bloody line. The way to picture where a force would go with moments. So let's there we are. So line up your ruler. The ruler is going to be essentially AB, the line AB, as you can see here. I matched it. Now, because we're taking moments at A, imagine holding one of your finger and fixing it at A, so the ruler doesn't move at A. Okay, so I'm holding it at this little circle point there. What I've did a little dot. That's where I would hold my ruler. Now, for each perpendicular force, mg cos theta, first of all, what would happen if I then pushed, that's mg cos theta, right? What would happen to the ruler if I pushed it down like this? it's going to cause the ruler to move anti-clockwise, isn't it? It's going to turn clockwise, if you can imagine that. So that'll be a clockwise force. So mg cos theta will be clockwise. So I'm going to say mg cos theta is going to go that way. But then what about the reaction force? Well, again, then the perpendicular component is acting that way. So if I push, so now if I imagine this angle, this force RB sine theta, the perpendicular force of RB up the line, then this line, imagine if I then use my other finger to push the ruler at that point in that direction, it's going to cause the ruler to go anti-clockwise, isn't it? So that'll be an anti-clockwise moment. So therefore, I can use that's using the ruler to work out the direction. So therefore, the anti-clockwise is RB sine theta. But also then want the distance. Now the distance was 2a, wasn't it, from A? AB is the length of 2a. And that's going to equal, because it's an equilibrium, again, the moment will equal the rate, the weight component, mg cos theta. That's the perpendicular component of the weight to the line. And that's halfway, so it's going to be just A. Well, I can simplify that a little bit. And say I could cancel an A out, so I can say 2 RB sine theta equals mg cos theta. Okay. And that's all our equations. These three equations are the only things we've got to work with. So first of all, it's asking for mu. Okay, so question A is showing mu is this. So actually, f is mu r. Actually, f will be less than or equal to mu r. Okay, it's not in limiting equilibrium. It's just an equilibrium. So remember, something with friction is an equilibrium. The force will always match the reaction until it exceeds something called a limiting equilibrium, where f equals mu r. Afterwards, then it'll start moving, but it's an equilibrium, but not limiting. So it's still less than or equal to mu r. Okay. So that's just something to bear in mind. Now we just need to get mu. So mu is going to be well, f over RA is going to be less than or equal to mu. Or in other words, mu is going to be greater than or equal to f over RA. So we need expressions for f and RA. Okay. Well, we know that f is equal to RB, but we also know that RB, well, this equation is going to be equal to a half mg, so divided by 2, mg cos theta over sine theta, right? But I recognise this is cot, isn't it? This is a half mg cot theta. So then what that means is f is equal to rb, so therefore f is also a half mg cot theta. And then I need RA. RA is simply equal to mg. So therefore, mu, if I substitute RA in, because remember, I did all the resolving up here. I'm just substituting the equations I've already got. So then, therefore, mu is going to be greater than or equal to. It's the right direction, isn't it? Yes. So that's going to be equal to F, which is a half mg cot theta. Because remember as well, cot theta, you should remember, like I said, pure is not over. They can ask any part of pure in mechanics or stats. You need to remember the trig identities. So cot theta is cos theta over sine. Okay, which is also 1 over tan. That's where I got that from, just to clarify. Because we have cos over sine, so we get a cot. So that's a half mg cot theta over, well, RA, which is mg. Well, the mg's cancel to be left with mu is less equal to a half cot theta. Is that what they wanted? Yes, it is. Lovely. Okay. Then it says a horizontal force of magnitude kmg is applied to the beam at A. This force acts in the direction that's perpendicular to the wall and towards the wall. I think it means, yeah, okay, perpendicular and towards the wall. So we added another force, so we need to resketch what's going on. And we need to do it all again. So that's F. Okay. I'm tempted to, yeah, I think I'm going to resketch this. It's looking a bit grim now, this diagram. Let's resketch what's going on. So B. So I have this line again. There we are. So that's A to B. Again, we have the angle L theta, was it? Yeah, it's theta. This is at B. You have a wall here. That's going to have a normal reaction of RB. It may or may not be the same RB. Again, this is going to have a reaction of RA. Again, then we have a mass of mg. Now it said that the horizontal force is applied to A, and it gave the direction. The direction is perpendicular, is towards the wall. So if we apply an A, it's either going to be that way or this way, kind of like friction. But if it's towards the wall here, it's going to go this way, isn't it? It's going to go this way. Did you call it? No, it was kmg, wasn't it? So that force is acting that way. So then friction, what's going to happen to friction? Now, originally, the friction was acting this direction because the reaction at B, hang on a second. Okay. Oh, I have a pen gone. Oh, there it is. Yes, so friction originally was acting that way to oppose the reaction here, acting the opposite way. But now we've got a force applying. So originally the wall will be tilted to the left because of the reaction at B. But then this force is going to oppose it and go the other way. So then it's going to move the ladder towards the left. So therefore the friction is going to oppose it and it's going to go that way instead. Okay. And that's all the forces added. So that's our new force diagram. And we need to create the new system of equations again. So we're going to resolve up, and it's still in their equilibrium, so we can equate the opposites together. So if we go up, then RA is again going to equal mg. That's not changed, if you remember. Here, that's not changed. If we resolve to the right again. We're going to get, well, what's acting to the right? The KMG bit here. And that's really it. So KMG, and then the opposite direction to the left is going to be the friction acting that way, and as does the reaction at B. So that's going to equal F add RB. And then we can also take moments. And actually, if we're taking a moment at A, that's not going to change. It's still going to be RB sine theta of 2A is mg cos theta A. So this equation here. Because RB and the weight and the reaction force would still resolve in the same way, they'd still be the same. So if we're resolving at A, even though all we did was add a force to A, but we cancel all the forces at A anyway, so it wouldn't matter. So then if we take moments at A, so if we resolve at A, so we take moments anti-clockwise at A, we're still going to get 2RB sine theta is going to equal mg sine cos, what was it, cos theta? Mg cos theta, there we are. So we've got our equations again. So again, we need to solve it to find k, is it? Is that what they're asking us to solve? Find k, yeah. But we're also given now mu is a half and tan theta is 5/4. But we also know, so we can also deduce f is equal to mu r now, because it's a limiting equilibrium. So f is at maximum friction, so it's going to equal to mu r exactly. So mu is a half, so f is going to equal a half of r, and it's going to be at A, so it's going to be a reaction at A. And there we are. So it's basically the same sort of thing. We just added an extra force here, but let's work with that. So to find K, but we're also given that tan theta is 5/4. So again, if we draw a little triangle here, theta, tan, again, SOHCAHTOA, opposite's going to be 5, adjacent's going to be 4. Now, the hypotenuse is going to be root 5 squared and 4 squared. Hate the hypotenuse. Put that in the calculator. You're going to get, you get root 41. Really weird. There we are. And it's better to do it this way because if you instead do inverse tan, it might not work nicely. You might get a mad decimal, and we need the exact values. So that's the best way to do it and the quickest way as well. Yeah, it's 5/4. It's really weird to choose that number. Anyway, so that means we can simplify it. So that means we can find RB again. So RB is going to be mg cos theta over 2 sine theta. So again, that's going to be a half mg cot theta. So cot theta, that's going to be half of mg. Now, that's cot theta again is 1/tan. But we know 1/tan, tan theta is 5/4. So cot is the reciprocal of 4/5. So that will go to a half times 4/5. We'll be left with 2/5 mg. There we are. So far on RB. We also know RA is mg. So therefore, the friction is going to be a half mg because F is a half RA, as we see here. And we know RA is mg. So then we're just left with the final equation. Kmg is going to equal F plus RB. So F is a half mg, and RB, which is 2/5 mg. So therefore, K is a half and 2/5. I'm just get rid of the mg, which is going to equal 9/10. And there we are. Lovely. Cool. So, like, yeah, like I said, like practice mechanics, the same forces every single time. It's the same process every single time. I do say mechanics probably the hardest part of the course, or when you learn it and practice it. But once you do practice it, you learn the questions. It's the same every time, you know. But yeah, cool. Okay, question 4, projectile motion. A small stone is projected at the speed 65 from a point O. The point O is 70 meters vertically. They're giving all that for us, and we're given an angle tan alpha. The stone hits the ground at the point A. The stone is modeled as a particle. Okay, so it's the same stuff every time. So we're going to need to set up a Suvat equation. So the time taken from O to A. So we're going to need to we're going to need to consider the vertical Suvat and the horizontal part. So the vertical Suvat, and that's going to go upwards from O to A. Okay, so positive direction, upwards is positive, and we go from O to A. So so how much displacement vertically has gone on? So it starts at 70 above, and it goes to 0 at the end. So the displacement is negative 70 because it went down overall by 70. That's the displacement, the overall change from the start, the overall difference in the height. So it's minus 70. For U, again, it almost like resolve the speeds to the horizontal component, which is going to be 65 cos alpha, and upwards is going to be 65 sine alpha. So the initial vertical speed is going to be 65 sine alpha. V we do not know. A is going to be minus G. Because we're assuming upwards is positive, but acceleration is going down due to gravity. So the acceleration is G downwards. So if you're going upwards, the acceleration would be negative G. And then T, well, we want to find T. T is question mark. So we have stuff to work that out. So again, we want the Suvat equation without V. We don't care about V. And that's going to be, again, S equals UT at a half AT squared. Again, check the formula book. There we are. And so plug our values in. Minus 70 is going to equal 65 sine alpha t at a half AT squared. So I'm going to say G is minus 9.8. So 9.8 divided by 2 would be left with minus 4.9. 4.9 t squared. Okay. But we can work out sine alpha. Again, we are given tan alpha is 5 over 12. If we construct a triangle of alpha, again, tan is going to be SOHCAHTOA, opposite is 5, the adjacent is 12. Obviously, 5 is opposite and 12 is the adjacent. And then if you do the Pythagoras of 5 squared and 12 squared, you get 13 squared. So the length of the hypotenuse would be 13. Therefore, sine alpha is going to be opposite of adjacent, and cos alpha is adjacent, so it's 12 over 13. Opposite of a hypotenuse and adjacent over hypotenuse. There we are. Okay, we're nearly at the end now. So then we can substitute in, say, but I'm gonna times by negative 1, so get rid of the negative. So 4.9 t squared minus 65 times sine alpha. Now sine alpha is 5 over 13. So 5 over 13 times by 65, you're left with 25. So it'd be minus 25t plus 70 equals 0. Well, now we've got a quadratic for t. So again, you can use a quadratic solver in your calculator, but if you want to show your working, just really quickly jot down a quadratic formula instead of using the solver. Just write it down. So t would equal plus 25, so minus b plus or minus square root of minus 25 squared minus 4 of 4.9, 70. That is a 70, not 6. All over 2 of a, which is going to be 2 of 4.9. And then, don't put that into the calculator. Then you can use a quadratic solver, which should be a lot quicker. But then you're showing you're working, you know what I mean? So that'd be 4.9 for A, minus 25 for B, and 70 for C. Oh, what's going on here? Oh God, I get a wrong imaginary number. Oh dear. Uh, oh, that's why this is minus 70. That's why. Because this, if I times by -1, this would then be plus 70, but then I'm moving it to the left, to the right anyway. So it then go back to negative. My apologies. There we are. So then if we take plus 70 to instead be minus 70, okay, you get a more reasonable answer. So t would be 7.111 or minus 2.0089. But obviously t has to be greater than 0, t is positive because it's time. So t equals 7.1 to 2 dp. Okay. Does it say to round it? I don't think they normally don't. Mechanics say they're fine anyway. I didn't read that. Deceleration 10. Oh dear. So instead of 9.8 for G, A is simply going to be minus 10. Because I did 9.8, that's going to change the answer. It was in bold as well. I didn't even read it. Oh my god. So then a half A, so it's going to be a half of minus 10, so it's going to be minus 5. Okay, so then 5t squared minus 20. There we go. So that would be 5 instead of 4.9. So then the values you get in that, if we then change A to be 5, you get 7 bang on. Okay, so you get 7 or probably -2 or something like that. I don't know. Or yeah, -2. Okay, but then t is greater than 0, so t's at 7. There we go. I didn't spot that. That's a good spot. Wow. Yeah, it's bold C. Acceleration is 10. So G is 10 that time. You do pay sometimes, yeah, they do expect you to give a certain value of G. So that'll go to 10 as well. Okay. Find the speed of the stone just before it hits the ground at A. So the speed is going to be obviously the modulus of the velocity, but we want the velocity at A, the overall. So we're going to need to consider the velocity at A in both components. So again, do that again. So vertical, do that, which is again positive from O to A. Again, S now is going to be again minus 70. U is going to be again, that's going to be uh 65 sine alpha. That's the original uh vertical speed. But we can simplify that, can't we? Sine alpha is 5 over 13. Yeah, so 5 over 13 times 65 will get us 25. So that will just go to U is 25. And then V, we want to work out V. And then A is going to be minus 10. And T, we don't actually care, but we already know what T is. We worked that out. So then to find the V, the velocity at A, the vertical suva. So then we want the expression from the suva equations that do not include T. So it's going to be this bit, isn't it? V squared is U squared at 2AS. So therefore, v squared is equal to u squared plus 2as. So v squared is going to equal 25 squared. Add 2 lots of minus 10 of minus 70. So put that in the calculator, you're going to get 25 squared. Add 2 lots of minus 10 minus 70. And you get 2025. That's fitting. So then v is going to be root 2025, which is 45. Plus or minus 45. But this is where you have to be careful because actually I don't think it matters at the end. But what's happened here is vertically initially it's going up, but then the speed at the end is going to go down. So the velocity vertically, because it's going down at the end of A, like the final velocity. So vertically is going down, and we assumed upwards would be positive. So V is negative 45 meters per second. I think it's in meters per second. But that won't matter because we only care about the number. If we're going to deal with what did it say? The speed. So speed is modular, so it's just distance of a vector. Okay, so we found the velocity at B for the vertical. Now we need the horizontal speed. But we know the horizontal speed anyway. So the horizontal speed is always constant because there's no acceleration in the horizontal direction. All the acceleration is vertical because it's gravity. Horizontally, there is no acceleration, so it's zero. That means if you were to say integrate 0 with respect to t, so integrate at the velocity, it would still be a constant. So you'd get 0 at c, where c is a constant. So it's constant speed, which means the speed is the same horizontally all throughout. But we know what the initial speed is horizontally. It's this 65 cos alpha. So it's always going to be 65 cos alpha. And so that's 65, and we know what cos alpha is. It is 12 over 13. And so that will be 65, 12 over 13, which is 60. Okay, so it's asking for the speed at A of the velocity. It's the speed at A. So that is going to essentially be the composition of the vertical and horizontal. Okay. It's exactly like the initial speed. So the initial, we split the 65 was the speed, really, but that was split horizontally at 65 cos alpha and 65 sine alpha. And so therefore we did the Pythagoras, you got 65 overall. It's the same concept here, but this time the speed or the velocity overall at A is going down. So if we were to draw the diagram here, let me get rid of this now. The speed essentially, again, it's going to go that way for the horizontal, but then the speed is going to go downwards, isn't it? So therefore, the final velocity, so v, the final velocity, that's going to be, well, it's going down by 45, so it's going to be 45 and 60. Right? Because remember, we worked out v to be minus 45, but the minus because it's going down. So therefore, the vertical component of the final speed is going down by 45, and it's going to the right by 60. That's the horizontal part. Overall, then, the speed is just going to be the Pythagoras of that. So it's going to be the speed at A is going to be the square root of minus 45 squared or 45 squared is the matter. But I'm going to say 45 because we're dealing with like a triangle. So 45 squared add 60 squared. And that will get us 75 at the end. And there we are. That's the speed. It says one limitation of the model is that it ignores air resistance. State another limitation. I went over this in the other mechanics paper, but there's a whole list of stock answers you can remember. So the common one is limitation is that could affect the reliability. Does not use a precise answer for G. Okay, so that means because G was rounded to 10, wasn't it? So that's the stock answer. Imprecise value of G. Also, does another one is does not consider variable acceleration. Okay. So obviously G was always acceleration was always G, wasn't it? But in reality, there's going to be a lot of factors. Acceleration, there we are. Spell. But in reality, it's going to be forces acting on it that will affect, the acceleration, such as air resistance, that will give it a more variable acceleration. So those are the two sort of answers. Um, but yeah, and let me look at the mark scheme again. And again, same sort of thing. I could also talk about probably how the stone was modelled as a particle that has its own problems because then you're assuming the particle has no dimension. But in reality, a stone is like 3D object, so it's going to have multiple dimensions, which again will affect how the air resistance will affect it as it moves up. Um, so that's another thing. And also, so what else are they after for that sort of question? Let's have a look. Um, yeah, an approximation value for G was used. The dimension of the stone could affect its motion. So yeah, because it's a particle, you're assuming there's no dimension, but actually there would be. The spin of the stone, no idea what that is. G is 10 instead of 9.8 have been used. Yeah, G was assumed to be constant. So again, like acceleration was constant, but it could vary. The wind effect and the shape of the stone. Okay. Um, there we are. Those are sort of answers, but those are the things I always copy down. The variable acceleration and the fact that G could be more accurate. Because again, G is kind of like an ongoing decimal, like E and pi. So you can always use more decimal places. Anyway, final question. At time t is seconds, the velocity is given as this, and it says A to simplify the acceleration. So remember, the acceleration is going to be the derivative of velocity. And so that's going to be the derivative. So that's going to be, well, V is in column form 3t to the half and minus 2t. If we're, if we're then going to differentiate the vector, well, you just differentiate it part by part. So 3t to the half will go to 3 over 2, t to the minus a half, and minus 2t will go to minus 2. There we are, simple, 2 marker. Find the value of t um, at the instant when p is moving in the direction of I minus j. So when it's talking about particles moving in the direction, it's saying that's referring to the velocity. So the velocity is moving in the direction of 1 minus 1. What does that mean in terms of an equation? That means, in other words, that v is parallel to the vector I minus j because it's going in the same direction. Well, parallel lines or vectors are the same direction. So that's what that means. Okay, whenever you see something else, a particle P moving in the direction of so and so, the velocity has to be parallel to that. And so we set up this equation where v is k1 minus 1. But we know that v in general is 3t 3t to the half and a minus 2t. And that's going to equal k lots of, well, we can bring the k in. That's going to equal, that's going to equal k and minus k. So essentially, this is now simultaneous equations to solve for t. So then 3t to the half is firstly k, and minus 2t is minus k. Well, if you just flip the negative, that will go to say that 2t is equal to k if you divide by minus 1. Well, that's an expression for k. So then we can substitute k into the other equation to get 3t to the half is equal to 2t. So then 3t to the half minus 2t is 0. Okay, now we can solve this. You can recognize, well, we can pull a factor of t to the half out, and then it's 3 minus 2t to the half equals 0. Why have we done that? Well, t1 uh, divided by t to the half is t to the half. And in other words, then, t to the half times by t to the half, then you add the indices to get t to the 1. Okay, so that works. If we were to expand this back, we would then get back t. If that makes any sense. Alternatively, if it really helps you, if you're struggling to see that, we should know t to the half is root t. So we could say 3 root t minus 2t is 0. Actually, it might be a bit tricky because you might be tempted to square it, but squaring it will add a solution that you might not want. I think it's best to stick with this, in my opinion. Yeah. Oh no, but you could recognise, well, if you say u is root t, then we're going to have 3u minus 2u squared is 0. So then you can factor u out, so u is 3 minus 2u equals 0. And then put the u back in, where u is root t. So that's t to the half of 3 minus 2t to the half. There we go, we get the same bit. Either or, whatever you're comfortable with, but there we are. So that means t to the half equals 0. So that's root t. So root t is 0, but then t has to be 0. Or 3 minus 2t to the half is 0. But that means 2t to the half equals 3. In other words, root t then is going to be 3 over 2. So then t is going to be 9 over 4 if you square both sides. Well, clearly t is greater than 0 exactly, because that's boring. When t is 0, uh, uh, um, it's kind of trivial because when t is 0, velocity is 0. So then that's saying k would have to be 0. That's kind of not what we want. Oh, there we are. It even explicitly says t has to be greater than 0. But it wouldn't make sense either. It would be such a pointless solution. But anyway, so t is greater than 0, so clearly t has to be 9 over 4. And that's the point where that's the velocity is parallel to parallel to that vector 9 over 4. Okay, part C. At the time t seconds, the position vector of P relative to O is r meters. When t is 1, r is minus j. So find an expression for r. So again, now we're given v. To get to r, which is a displacement, we're going to have to integrate, aren't we? So we're going to have to integrate v dt. So what's that going to be? So remember, v again is equal to 3t to the half and a minus 2t. right? Yes. So then again, like with differentiation, you integrate both the parts separately. So first is the integral of 3t to the half. That's we're going to add 1 to the power, so that's going to be half add 1, which is 3 over 2. So that's t to the 3 over 2, and then we're going to divide by the power. So 3 divided by 3 over 2 is the new coefficient. So then minus 2t will get to integrate to t squared, and then we'll divide minus 2 by 2 to divide by the power. So that will go to 3 divided by 3 over 2 will get me 2 t to the 3 over 2 and minus t squared. But also, when we integrate both of them, we're gonna have a new constant as well. We're gonna have a constant plus c and another constant plus d. But if we're adding another number to both parts, that's the same as adding a vector, right? In general. And when we integrate a vector then like this, we add a constant vector to compensate, okay, for the integration. So we need a condition like with normal integration, but we are given when t is 1, r is minus j. Well, that's 0 minus 1, okay, in column form. And that's when t is 1. So when t is 1, r is equal to 0 minus 1. Therefore, 2 lots of 1 to the 3 over 2 minus 1 squared, substitute 1 for t in, add c is going to get us 0 minus 1. So that will simplify to 2 and minus 1 plus c is 0 minus 1. Therefore, c is going to be equal to 0 minus 1 minus 2 minus 1. And therefore C is going to equal to, and then 0, then we subtract the parts together. So 0 minus 2 will get us minus 2, and then minus 1 minus minus 1, so minus 1 add 1 will get us 0. So then let's restate it. Our overall displacement vector R is going to be 2t to the 3 over 2, but then we have this component of minus 2 afterwards. And then we also have the other component of minus t squared, but there's a 0, so we add in 0. That's pointless, so we just leave it there. And there we are. That's our expression for R. And then part D says find the exact distance of P from O at the instant when P is moving with speed 10. So the speed is 10, while the speed again corresponds to the velocity, the modulus of the velocity. Because if we take the distance of the vector or the velocity, that will get us to speed. So that means then that therefore mod v equals 10. Well, the modulus corresponds to the Pythagoras of the two components. So the square root of 3t to the half, all squared. First of all, so that's going to be 3t to the half, all squared. Add then the other component of minus 2t all squared, right? And that's going to equal 10. We can actually get rid of the square root by then squaring both sides. So then that simply means 3t to the half all squared add minus 2t all squared is equal to 100. And now we just need to simplify the brackets. Well, 3t to the half all squared, again, you can use your index law here. A to the m of n, you times the powers together. So 3 squared first is 9. T to the half times 2 is t. So t to the 1, which is t. And then we're going to have the minus 2 t, that's going to be add 4t squared, right? And that's going to equal 100. Well, I'm going to take 100 away because now I know it's have a quadratic. So 4t squared, 9t minus 100 equals 0. Again, I'm going to quickly note the quadratic formula just to fully show my working. So t is going to be minus 9 plus or minus the square root of 9 squared minus 4 of minus 100 over 2 of 4. And so then I'm going to put that then into the quadratic solver to save time. So the polynomial solver of 4, 9, and minus 100 to get t's 4 or minus 25 over 4. But again, t is positive. So therefore t is 4. So that's the value of t now. That's cool when the speed is 10. So we need the distance from P to O. So what's going on? So, like I said earlier at the first question, I think it was, when we have variable acceleration, the displacement vector r is now giving us the position vector. Okay, so so that's what we want actually, because then at t is what was it? T was 4 seconds. If we substitute that into r to get r4, that's giving us the position vector, so the vector between O to that point R4. If we then we can find the distance from P to O, so that would be P. So from P to O, we can then do again the modulus, the length. So then I'm going to substitute T as 4 into R. And I'm going to get R is equal to, so we did that in part C. So it's going to be 2 t, which is 4, to the 3 over 2 minus 2, and then the other component is minus t squared, so it's going to be minus 4 squared. So that's going to be the vector. If we plug that into the calculator, first of all, 2 of 4 to the 3 over 2 minus 2 would get me 14. And then the bottom bit would be minus 16, right? 4 squared is 16, then minus it. So that will give me the position vector at t is 4 relative to O. So therefore, distance from O is going to equal, or is, the modulus of 14 squared add minus 16 squared. And so that will be, put that into a calculator, 2 root 113, I believe. And there we are. Cool. There we are. Good. Not up to, the algebra can be a little bit tricky, but final question, not too bad. I think there were harder ones in here. I'd say question 3 could be pretty tricky. But yeah, not too bad all in all. But yeah, so now I've covered the mechanics bit again. So I've covered stats and mechanics again. Now, hopefully this session proved useful. I'm going to end it there and try and upload it as quick as I can to give people enough time to see and do whatever they want with this for the exam tomorrow. But that's really it. I'm not. I think that's all for now. I think I've covered a good portion of questions between the two sessions that could probably cover the skills you'd need to apply. But hopefully you realise now that actually, what's it called? The questions are very similar. Like I'm repeating the same sort of methods and the same points every time. Well, not every time, but for most of the questions. And that's a good thing because it's showing you, you know, how to tackle questions in the exam because it'd be quite similar. But yeah, I'm just going to leave it there. Good luck. It's over for me as well because there's no more like paper revision sessions to do. This final maths exam really now. But yeah, good luck. Obviously, hope you get the grade you need for whatever you want for A-level maths. And yeah, good luck, and I'm gonna leave it there.